All right, welcome back, everyone. I hope lunch was okay. Sorry if you had an issue getting food. I know the lines were a bit crazy out there. First up, we have Peter Stone with Sony AI and UT Austin. Welcome, Peter.
All right, thanks for the introduction. Thanks all for being here. So as I said, I am coming from UT Austin and Sony AI. I'm going to talk mainly about a recent result from Sony AI on the first robot that can beat a professional athlete at their own sport. So I'll talk about that mainly. But first I'll tell you I am coming from UT Austin. In 2 weeks I'm going to be the head of a new school of computing there that brings together 3 different departments. I was the founding director of Texas Robotics. We're going to be hosting the conference on robot learning this fall in November. I hope to see many of you there. And if you come, you'll get a chance to see our beautiful new robotics facility, Anahis Gym. It used to be the women's gymnasium when there was such a thing as women's gymnasia, but now it's filled with robots. We also have a machine learning laboratory. I'm deeply involved in an ethical AI initiative called Good Systems. And I'm really proud of the AI education that we've been doing there, including a publicly available, anybody can use full course on AI literacy, essentials of AI for life and society, that's for non-majors or anybody really, and also an online master's for $10,000. My research is fairly broad, but the question that unites sort of all the things I've done over the years is this one: to what degree can autonomous intelligent agents learn in the presence of teammates and or adversaries in real-time dynamic domains? So my group publishes in sort of the sub-areas of AI shown here, especially multi-agent systems, robotics, and reinforcement learning. And some of the applications domains that I've used over the years have been things like robot soccer. So here's a video from many years ago. Our team was the one with their hands behind the arms behind their back. We ended up winning this competition with the Now robots, where you have to remember these robots are fully autonomous. The goal of RoboCup is by the year 2050 to have a team of humanoid robots that can beat the best World Cup team on a real soccer field. We're not quite there yet, but things have advanced since that video. Just a month ago, our team is shown in blue here. These are sort of bigger and faster humanoid robots. These are made by a company called Booster. It's a beautiful robot, but then we did all the programming, and it's a learned skill here of walking and kicking using reinforcement learning. Gotten to the point where we can now it makes sense to put humans and robots on the same field. So here's a clip where I take the ball and leave the ball for the robot and see what happens. The robot's able to turn and score a goal. So I also work on general purpose service robots, so things like this. At RoboCup, there's also a competition called RoboCup at Home, where a robot has to do things like putting away groceries, setting the table, interacting with visitors. And so this is a great domain for general purpose robots. And then prior to this, the table tennis result that I'm about to talk to you about, my team at Sony AI had a paper on the cover of Nature about 4 years ago, where we were the first AI agent to be able to beat the very best humans at a real-time control task, in this case, Gran Turismo. So in this video, the green cars are trained with end-to-end reinforcement learning. The white ones are driven by some of the best drivers in the world at Gran Turismo. We outperformed them, and that was featured in Nature. And now I also work on also navigation, not just in road settings, but in more social settings. This is joint work with Joydeep Biswas, where we have robots navigating through the sort of hike and bike trails through Austin, having to navigate social situations. But the title of my talk and the main thing I'm going to tell you about is a result called ACE with my team at Sony AI. Oh, one other thing I wanted to tell you about, because we just publicized it a couple days ago, is a data set that we're collecting called Oopsie data, which is about robot failures. So most data sets are about robots doing successful things. This is a community-sourced effort to try to gather failure data from robots, and we hope that many of you will contribute to this. So look it up. There's a way to contribute and annotate what the failures were. Postdoc in my lab, Klaus Volker, has been leading that. But the main topic of this talk is trying to create a table tennis player with this group at Sony AI. Of course, it's not just my work. It's a large team. It was led by Peter Duer. He's really deserves the lion's share of the credit here, but a huge team effort. It was featured on the cover of Nature in April 23rd, so just 3 months ago or so. And so you can read all about it there and get all the details. But the motivation here is that games have been a benchmark for AI for many years in sort of turn-taking settings like chess and Go and poker, and then some more real-time settings. As I said, GT Sophie was the first real-time control task where humans did better. The first real-world outperforming the best humans was drone racing. That was Davida Scaramuzza's lab. That was also featured on I think, a cover of Nature. But that was not in a sort of competitive head-to-head setting. Meanwhile, table tennis is sort of one-on-one, adversarial, and has been used as a motivator for robotics research for many years. Going back to the mid-1980s, this is a video from Google, and Vincent, who's the next speaker, played a role in this one, where a robot was sort of playing very well in a cooperative kind of setting. But there had been no example of a competitive robot that's able to beat expert-level players using Olympic rules. And so in this video, I'm going to show you our robot on the right is playing against a woman who has twice won an Olympic silver medal. She was once ranked 5th in the world. I think at the time we played her, she was ranked 11th in the world, something like that. And the robot is playing according to professional regulations. So the player's area is the same. The robot has to serve the ball, which has not always been the case in systems. So it has a cup where it can toss the ball up and serve it. So I'm not going to be able to go through all the details here, but the general system setup is that obviously it's not a humanoid robot, and it's so the form factor is that we actually built the robot, custom made, and engineered it to be as light as possible. It has to be able to move hit the ball 20 meters per second every 0.8 of a second. That's to get to professional level play. The cameras are all around the system. There's 9 that are positioned to get the XYZ coordinates of the ball, and then 3 that are event-based gaze control cameras that can track the spin of the ball, which I'll show you in a minute. And this is an overhead view where you see the player area and the robot workspace. The only concession that we make to this being a robot is that we don't allow the player to cross the net for safety reasons, but otherwise it's effectively regulation Olympic rules. The robot learns to play in simulation. So the 3 main contributions in the Nature article are the perception system, the reinforcement learning for control, and then the hardware of the robot itself. The main control problem for us was figuring out, as the ball is coming in, how do you move the arm of the robot to be able to hit the ball given a particular target and spin that you want to realize. And we call that a skill, as opposed to tactics, which would be choosing where do you want to hit the ball, or strategy, which would be longer term. What do I want to do from point to point or even game to game. So the most of our RL is at this low-level skill level. Much of it in simulation, but where the data is, it's a physics-informed simulator. Sorry, I keep jumping. The physics-informed simulator where there's data from the real world that builds the noise model, the ball distribution model, and the physics model. And then there's an actor-critic where it's asymmetric. There's a true state given to the critic, and a noisy state given to the actor, and then the actor is what runs in the real world. I won't go into one of the big technical things we needed to do was come up with an action space that the robot could deal with. So, because it's a 6 degree of freedom arm on 2 degrees of freedom for the base, and so there's a very sort of counterintuitive set of space points that the end effector could get to, and we find a way to map that to a sort of a hypercube, such that any point in that hypercube is a feasible. So we call this feasible action for optimal control. And then there's a model predictive controller that controls the end effector to try to get the target that is chosen by the reinforcement learning agent. So this video will show you sort of how the robot can react quickly you're going to slow it down and see as it hits the net, the robot was trying to hit a forehand, but then after the ball hits the net, it adjusts and then swings its arm back the other way and is able to still hit the ball back. So here it's again in real time. Whoops! In real time, you'll see how quickly the robot responds, and we have several examples on the blog and on our website showing examples of the robot responding to these net balls in real time. I said there's the event-based camera that's tracking the spin. There's no artificial marker on the ball, so it's just using the logo that's there. So here's what that event-based camera sees as the robot is spinning. So the mirror shown here on the left is tracking where the ball is in XYZ coordinates, and then in real time we're able to determine the speed and the spin of the ball, which is then given as input to the RL agent. This is a robot video where you have to slow it down to be able to watch it. Most robot videos, you see them sped up a lot. Here's a nice video from the viewpoint of the robot. It's a camera mounted on the arm and again slowed down. So you can see it's tracking the spin and speed of the ball and then deciding how it should hit it. I said the other contribution here was the robot itself. It's a custom-built robot where we use an optimization process to sort of take away all of the mass of the robot that isn't needed for structural stability and reduced it 5 kilograms from the original design so that we could achieve the high speeds at high frequency, where there's 6 revolute joints and 2 joints on the XY plane on the base. And then there's also a serve library that's done using an evolutionary process where we get a diversity of serves, so it's not predictable to the player, and so and then the robot will pick one of them to execute, but it's trying to find some that have backspin, top spin, different locations, and all of those are trained in to be able to sort of start off the point before it moves to the standard RL controller for the rest of the rally. Just in terms of results, the Nature article has results up until December 2025, where we were losing sometimes, but beating some university level players. The ones shown in red are losses. The ones in green, we won at least one game against them. If there's a T in the top, that means they're a professional level player. And then recently, just a month or so ago, we released a blog with all the results from this past spring, where we did beat a woman who was ranked 5th in the world at one point, a man who was ranked 99th in the world at one point. So really beating professional level players. And then this is just showing some of the data of how fast the ball is being able to hit, both back in April 2025 and 2026. We're hitting the ball slightly faster than professional humans, not quite putting as much spin as professional humans. And this is showing just another match against he was, I think, ranked 99th in the world. Male professionals hit the ball harder than the female professionals, but we're able to beat him as well, even at really fast speeds. And so all of these videos are available online. And I'll just, in summary, in this video, which will be the last one I show, is a warm-up video. It's the first time this professional woman was playing with the robot. And so it's not trying to beat her. It's like sort of this warm-up phase. But you'll see at the end of the point that she's really having fun, is really impressed and enjoying herself. But the summary here is that for the first time, we've shown that AI agents can reach expert-level performance in tasks that require fast, real-time decision-making in physical space. There's still many open questions. Can the robot beat the world champion? We don't know. Can expert table tennis players use these robots to improve their game? We actually do have some examples already of professionals getting ideas of shots that they wouldn't have otherwise tried. And could we do this with a humanoid? I think we're still very far from that. There's, like I said, lots more information on this online. And there'll also be a talk on the main stage at 3:10, I believe. Mika Spranger is the president of Sony AI. He has a 10-minute talk. He'll talk a little bit about this and some of the other projects at Sony AI, including more about GT Sophie, the high-speed racing agent. So with that, thank you for your attention. I'll be around if there's any questions afterwards.
All right, thank you, Peter. Next up, we have Vincent Van Oak, and he is with Waymo. All right, Vincent, you want to come up?
Thanks for having me. I hope that for this crowd, I don't need to introduce Waymo, but if you don't know, Waymo is an agentic AI company, because of course, except our agents are big, beautiful hunks of metals that have 4 wheels and are driving around in your neighborhood. We have, by now, thousands of agents operating in the real world, doing very long horizon tasks to completion and serving real customers, paid customers, completely autonomously. We're right now in 11 cities, but we have ambitions to expand to many cities in the US and abroad as well. Our goal really is to provide autonomy at scale and to become the world's most trusted driver. I like to always show this notion of trust as a central feature of the Waymo story, because it's not just about safety. It's about consistency. It's about repeatability. It's about predictability. A lot of the same features that are factors in the trust that we place in agentic agents in general. If you're already tired of my joking around about the parallels between autonomous driving and agentic AI, I'm sorry, I'm just getting started. There is actually a lot of parallels to be made between physical AI on one end and agentic AI on the other hand. Like if I talk to my roboticist friends and they look at what's happening in the world of agentic AI today, they really look at it with a smile, because all of the hard problems that we've been experiencing in the past 20 years in robotics are exemplified in agentic AI. Right? It's really about how do you build a system that has enough affordances to do things that are interesting in the real world, but that also you can trust, right? And that can evolve in the real world doing real tasks safely and with a good stability and consistency. And all of those problems were first really exemplified in the physical AI world and are now hitting the agentic AI world. So I want to take a few lenses to look at agentic AI from the perspective of somebody who's been looking at physical AI for a while. And one lens we can take is the lens of industrial automation. Right? So industrial automation is traditionally the art and engineering behind taking a whole bunch of components that are all, mostly do their work, but will occasionally fail, and stringing them together, like on an assembly line, for example, and harness them to provide very high levels of reliability, safety, autonomy over very long time horizons and at scale. Right? There are lots of lessons that we can draw from industrial automation for agentic AI. I'm just going to, pick one. Right? One of the lessons that I've seen in this space is that it's all a game of nines. Right? At a certain scale, you can get away with 99% repeatability. As soon as you scale up, you need to go to 99.9 or 99.999 and so on and so forth. Every 9 typically means you need a different solution. Every 9 that you earn is not earned by just improving your system a little bit, getting a better model, or reducing the error rate. You have to redesign your system for the level of reliability that you want. So another angle that we can look at agentic AI from the perspective of physical AI is the angle of autonomy. Right? So in autonomous driving, we have those 5 levels of autonomy. You start from no automation to driver assistance systems. Waymo operates at level 4, very high automation. If you think about coding agents or AI agents, there is this kind of same gradation of, you write your code by hand all the way to you just YOLO it and just let the agent write everything for you. One of the lessons from AV in that space is that level 3 is a weird beast. Level 3 is not a very pleasant place to be. Right? It's very bad for cognitive load. It's very bad for safety. It's very bad for productivity. And we've seen this in agentic AI as well, when people started moving from code completion to agents and having this kind of mixed scenario where sometimes the human is in charge, sometimes the agent is in charge, and this interface between the two is very uncomfortable. The other thing that we've learned in the AV space is that level 2 and level 4 are very much different beasts. So the very different design decisions, very different approaches, and you can't really just graduate your way from a level 2 to level 4. You have to rethink your system dramatically. And we're seeing that in agentic AI as well. It's not the code completion systems that you used to use are not exactly a simplified version of the agentic systems that you use today. Another lens that we can take is more of the dynamical systems perspective, right? So there's a lot of work that's been going on in control theory in the robotics space, where you study essentially nonlinear dynamical systems. And agentic systems are essentially extremely nonlinear dynamical systems. So maybe a lot of the physical math that goes on there is not translatable, but the concepts and the way of thinking about it, notions of observability, controllability, stability, realizability, that last one is, can you actually do the task? All of this is actually very relevant to the task. One of the lessons in that space has been, and it's a lesson that has been, sort of adopted by, the agentic AI world from the start, is that if you want to optimize for closed loop behavior, meaning if you want to optimize for long horizon, you need a very different reward system than if you're trying to optimize for open loop. So in the robotic space, this is something we call the dagger problem, and there's many names for that in different fields. It's the idea that if you have a system that is a multi-step system, and you're trying to minimize the error at every step, you may end up in a place where you end up making very correlated errors, and at the end of the day, your system ends up in a very different place than where you want to take it. Right? So optimizing one step at a time hasn't really worked. That's why we do long horizon planning. That's why we do reinforcement learning. That's why we think of long horizon tasks with the different objective functions. One of the ways that we approach this problem is by optimizing one step at a time, but by imagining the future and by looking at the long horizon and dreaming up what the long horizon would look like if we took a specific action. That's where basically world models are coming into play. And so at Waymo, we've been working on world modeling to optimize our system for long horizon planning. We have our own world model, which we've called the Waymo world model. We're very, very creative. And that enables us to do evaluation and simulation of long horizon behavior for our system in closed loop and with very good fidelity. So a few of the ingredients of a world model are, well, first and foremost, realism is a big part of it. The way we've approached it is we started off from a very good video generative model, Genie 3, from Google DeepMind. As you can see here, it's got some notion of physics, but it's got all the notions of physics. It can handle Minecraft physics as well as real world physics, but we really want our world model to follow real world physics, not just video game physics. We also want the model to handle the real world generative visuals, not just video game visuals. So we've basically taken the model and fine-tuned and adapted it to the Waymo use cases. So in this case, you see we have all the cameras that are on the Waymo car. You have the LiDAR. We've grafted LiDAR generative capabilities onto the model as well. And we're able to, this is a 30-second rollout of a completely imagined scene from this world model. Another important factor in world modeling is controllability. You want to be able to imagine counterfactual events. You want to dream up what is possible if you take any action. And so you don't necessarily want to follow exactly what has happened in the real world. For example, you want to change instead of turning right, you want to turn left or go straight, and still have the model render essentially something very high fidelity. And so we're able to generate, imagine new scenarios that are very realistic, irrespective of the action that we take. We also want to be able to control different aspects of the scene. So through language, we can say, hey, generate that scene in the morning, generate the same scene at night, change the weather conditions. You can have cloudy weather, foggy weather, change the appearance of things, change the general conditions. We want to be able also to very finely control the scene at a very fine grain. Imagine if you move a car from one lane to the other, what would happen as a result? So we have in the controls, basically, we can condition the entire model on all the cars, all the pedestrians, all the lane geometry of the model. And then the next stage is really about generalization, right? If we only are able to simulate the kind of data that we see in the real world today, it has some usefulness, but really having a world model really shines when you're able to go and extrapolate in scenarios that you've never observed or that you potentially never want to observe. So we've never encountered an elephant on the road. But we would love to be able to simulate different, animal encounters like this. One funny aspect of this is that if you do nothing and you just train the data on Waymo data, Waymo has never seen an elephant on the road. So you say, give me an elephant, the model will give you no elephant whatsoever. If you try to tweak it to improve its generalization and world knowledge capabilities, it will try really hard to give you an elephant, but kind of fail in funny ways. You have a elephant-looking truck, because it knows about trucks very well, and it has some notion of an appearance of an elephant, but it can't quite, square the two together. And then if you do it right, then you can actually have a full-on elephant on the road, and the model really understands the different things. And what's interesting is that, our LiDAR has never seen an elephant, but it's able to generate very reasonable LiDAR renderings as well. So we can simulate scenarios like what happens if we drive through a raging fire. We have never experienced that, but this is not a completely implausible scenario. We can simulate having snow on the Golden Gate Bridge. We can simulate having somebody in a costume walk by us. So this is actually a very realistic scenario. Every Halloween we will see people in costume walking around in various stages of inebriation sometimes. So we want to really, zoom in on, hey, this thing that you see on the road here, that's actually a human being. That's a very vulnerable person, right? And so we want to make sure that our system recognizes that this is something to pay attention to and to drive safely around, not just a random moving blob that moves on the street, right? There is actually a very significant amount of safety that really derives from us understanding the semantics of the scene, and we need to basically be able to validate that. Okay, so this is I only have 15 minutes, so this is a very high level, but I really want to stress that there is some interesting connections between physical AI and agentic AI. I think physical AI is agentic AI taken to the next frontier. Lots of lessons that can be learned from robotics, from automation, from autonomy that can be applied to non-physical agents as well. World modeling is a very interesting direction in general. I want to ask the audience that is working on virtual agents, what is your world model? Or do you have a very good high fidelity simulation of your environment? Because that's a key to being able to do long horizon planning and building some resilience and long range autonomy into your system. With that, thank you.
All right, thank you, Vincent. Next up is one of our very own, Trevor Darrell with UC Berkeley.
Thank you very much. That was, Vincent's talk was the perfect precursor to my talk, because I don't have to spend any time explaining to you why I am interested in physical AI. and I'm going to tell you today about recent work at UC Berkeley.
There you go, okay.
Yeah,
I wanted to make sure.
I saw it there. On real-world reasoning agents, and in particular, agents that can see, feel, and reason about the physical world. I mean, we already have agents that can see, but they actually don't always see that well, right? If you look at the visual encoders in today's VLMs and agentic VLMs, they're well designed for internet vision tasks, but they're not always that well designed for physical AI tasks or even precise internet vision tasks. Like, you can take an image, put it in a visual encoder, run it through an LLM and get a nice caption. You get another image, run it through the same architecture, and maybe get the same caption. You probably didn't realize those two images were actually different, but you got the same caption out of these encoders. I mean, do you realize these are different images? It's actually hard to see. And you probably have to look back and, there's some small details there. And you probably have to look back and forth between the images to actually notice the difference. And that's exactly what we don't allow most visual encoder architectures and VLMs or agentic AI systems to do. So let's do it. That's what we did. So we engineered a new representation we call a stateful visual encoder that's specifically designed to look for small differences or what we call state changes in the world, specifically in images here, but it could generalize to other signals as well. So here's a basic visual encoder diagram. Take an image, encode it, or push it through a number of layers to encode it, and then put it into an LLM. We make a very simple modification, so simple you'd be surprised that it's novel, of allowing cross image weights in the middle layers of the encoder to specifically be tuned to detect changes that are too small to normally be encoded in the representation. And with that, you actually can have a change encoder give you a very detailed caption, mention what's changed, or if you need to see whether a little box has been checked or not in a web interface, it's much, much easier to do this without tremendous brute force attack. How do you build this general idea? There are a lot of different approaches. We compare them all in the paper. I won't go into details, and I'll refer you to the paper. It has significant improvement in a variety of real-world tasks, like medical image report generation, or image editing control, or geospatial image change detection. And we have lots of result tables, as you would expect, in our wonderful project page and paper. Please check it out if you're interested in that, stateful visual encoders. So that's the seeing. I want to explain the broadness of the interest here. We go from seeing, manipulation, touching, and eventually reasoning. We want to manipulate things in the real world the way people can. Huge challenge of physical AI right now. Robots generally can't do these things. We want to be able to screw a light bulb in and have it turn on. And I'll show you our work on this that's called T-Rex. This is in collaboration with colleagues at NVIDIA. Current foundation models are amazing, right? They can reason, they can plan, they can act, but they're still not so good at reacting. And tactile is still the underappreciated modality. Certainly a lot of real roboticists know this, but a lot of the sort of AI roboticists think, oh, you can scale your way out of it without actually understanding dynamic forces in the real world. I'm not sure that's right. Human intelligence is dual process, and we really need agentic systems that are dual or triple process. We need this idea of a slow, fast architecture. And so we've embodied all of these ideas in our approach we call T-Rex, both a data set, data collection, and an architecture that has multi-process, dual process architectures, has tactile sensing and reactivity, and it can learn both how to feel in the dexterous manipulation sensor, and for example, a sharper hand, which is what we use, when to change the forces based on what it feels, when to adjust the slip to catch something that's about to slip, or put just enough pressure on to peel a card off of a deck. This is our platform, and here's example of our performance. So you can see we have 2 sharp hands, we have cameras mounted on the head and the wrists, and you can see the readout of the tactile sensors in the lower right tile. And we can do tasks that previously were impossible for previous approaches that didn't have tactile reactive policies. For example, squeezing a toothpaste out of a toothpaste tube. We did not actually yet ask the robot to brush its teeth. Maybe next time. Here it has to feel to sort of separate the 2 cups out of a stack. Here it's actually feeling the tile to actually recognize which of the 3 types of tiles it is just by the feeling of the indentations on the tile in Mahjong. And here it's able to grab a key and insert it into a lock and twist the lock. I think this is a little bit overnamed. It's not. It's really just pipette manipulation with liquid, and our T-Rex model can squeeze the bulb to push just the right amount of liquid out of it. Here we can extract a card out of a deck, and I think finally we get screwing a light bulb in. I think is the final example. And it knows how to put enough pressure on it to not crack the light bulb. And those eggs that I mentioned earlier were all real eggs. They were not hard-boiled eggs. So if you're interested in this, I encourage you to look at our webpage and paper, and importantly, our data set, which may be one of the most important artifacts of this project, Berkeley project with strong collaborators from NVIDIA. Last but not least, I want to talk about world motion models. How do we now reason in 3D in a very abstract way? We all know how to predict the 4D future. We can look at the world, look out at a car, see maybe key features on the car's wheel, and we can imagine how those are going to move in time. And now we can build, and we've seen earlier today, amazing world models that are generating live video pixels of predict every pixel in the future going forward. It's wonderful, but if I just want to maybe adjust something on that wheel as it goes by, or tighten a bolt on the wheel like a F1 pit driver, a pit crew, I don't need to predict what the trees are doing. I don't even need to predict what much of the car is doing. I want to predict the affordance or the geometry or how that wheel is moving over time. What is, what was, what is, and what will be across time. So this is our latest work on world motion models, where we build a motion model of dynamic 3D world trajectories. It's actually a world motion model over SE3 trajectories. It's poses, for those of you who are sort of geometry literate. And so much of the physical world can be abstracted as the motion of rigid frames evolving. And ours is the first very general framework for predicting and completing and eventually doing things like MPC over this representation. So we have a general model where we've tokenized the 6 degree of freedom pose frame and have it stacked over time with multiple different reference frames, one corresponding to all the different objects or rigid portions of a body in the scene. So this is a world model over SE3 poses. We call it a world motion model. Other than that, it's very general and in many ways the same as a world model that generates pixels. We train it by denoising sequences, and we can run inference either to predict the future given the past, to predict the future conditioned on actions given the past, to in-paint or motion plan, or to retarget, solve for dynamics, et cetera, et cetera. And we have a very efficient neural network architecture, transformer-based architecture that does this. I'm just going to show you in my 1 minute left some demos where all of these are being modeled by our world motion model, and you can, given text, cause the robot to learn motion trajectories to solve a certain task, either directly or using something like motion predictive control to solve the motion. Here's examples with the Amono data set, where we have human-object interaction, and we need to generate the motion of a humanoid in order to perform a manipulation task on an object in the world. our model outperforms baselines on that. And similarly, interacting with the world with objects and hands. So you've seen quite a diversity of different projects. This is world motion models. It'll be on archive soon. Keep your eye out for that. And I only showed you a few of the applications. Others are hinted on the bottom of the slide. Very general model, very cool. That's all I wanted to cover today. Give you a teaser on 3 great projects at Bear that see, feel, and reason in motion about the real world. Thank you.
Thank you, Trevor. Next up, we have Manmohan Chundrakar from UC San Diego.
So that's it.
Yeah, make sure we help you all set.
Hey everyone, it's good to be back at Berkeley. I'm going to be talking about autonomous agents and maybe a little bit about humans too. All right, so I think all of us here will agree that physical AI lives in the open world. We have endless edge cases that arise after deployment, and we have teams that go into continuous discovery and development loops to fix these edge cases, and all of these must be fixed with traceable release evidence. Now, the physical world is also rapidly becoming executable, right? So we have all of these CI/CD frameworks that can continuously run loops. We have agents that can deploy code. We have simulations to bridge gaps to data. And all of this points to a future of self-improvement. However, physical stacks are complex and require real-world experimentation. Right? And a lot of real-world knowledge, human expertise, is something that lives beyond static data. It requires us to have scientific ideas. It requires us to have expert workflows and physical interactions with systems. All of this means that experimentation and discovery is something that requires a lot of compute, a lot of data, and a lot of human talent for us to run in physical workflows. So in the next few minutes, I'm going to be talking about making autonomy autonomous in collaboration with humans, and how we can have discovery frameworks that are grounded in execution, how we can reflect human intent in agentic workflows, and hopefully sustain participation in AI-native economies. All right, so let's take this example scenario. Suppose you have an autonomous driving team, and you observe that you have an issue with perception for pedestrians. That would go to a simulation team who would need to figure out a way to handle these. Maybe pedestrians are thin structures, and it requires us to have better 3D reconstruction. So the team can come up with, let's say, Gaussian splatting or a new method for Gaussian splatting that can then be validated on real data, and eventually they can write a paper about it or publish a spec sheet. Now, what if I told you that this whole process is something that is run by a team of agents? The only input that comes from the developer in this case is to generate ideas to improve 3D.js to work with pedestrians for autonomous driving, test it on a particular family of GPUs, validate it on real benchmarks, compare to baselines, and publish a paper. So the team of agents here plays a set of specific roles. In particular, they produce research that is verifiable. They deploy code that is executable. They come up with ideas that are grounded in the physical world, and in general, follow a process of scientific discovery that's traceable and verifiable. So let's look at how this works. You have the input come in. The agents define the task that must be solved. In this case, OmniRay, a framework from NVIDIA, is something that they decide to improve upon. They come up with hypotheses for dimensions where improvement is possible. Specialist agents then launch a set of different experiments. All of these experiments are evaluated, that is, they are validated and falsified on an ELO rated tournament. Eventually, there's one idea with the highest ELO rating that would survive. This is a new method that comes up in this case, which has been implemented on real GPU hardware, so the gains are measurable. It is something that can be evaluated on real benchmarks, and then a team of writer and reviewer agents can come in and write a paper about it. So how good is the system? Well, so we took a few of these papers, and we submitted them to a CVPR 26 workshop on physical AI related topic, and with permission of the organizers, by the way, we are not trying to game the system. But 3 out of 4 papers that we submitted did get accepted. One of the papers got high praise. The paper that was rejected did have formatting issues with the equations and all, so we believe reviewer 2 in this case. But overall, this is not a system which is just for ideating and for writing papers. It's a system which is performing traceable and verifiable scientific discovery. So how does this work? Everything rests on a verifiable substrate on top of which we can work. We define a context-free grammar, which allows us to come up with ideas that are grounded. Every candidate method is something that mutates on top of a verified reproduction. Right? So everything is something that we can measure. It's something that we can validate and falsify. Finally, every claim that is made by the system is something that we can trace to a real log or a real line of code, a real GPU run. So the central engine that drives all of this is essentially this verifiable substrate. And how do we go about building this? Essentially, we reverse engineer the process. So suppose we have a knowledge repository, suppose we have papers. Can we then follow this scientific process to come up with the code that wrote this paper? Right? So how does that work? Let's take this example. We have a paper out here that has never been publicly implemented, so it's not like Cloud or GPT knows about this paper. We analyze the paper, we determine what are the new ideas, what are the factors that are giving us improvements over baselines, and those are the things that are then produced in the code for this paper. The code is something that is physically verified against real data. Improvements are suggested for the code, and this is something that we can then validate on real benchmarks by comparing to real data. Right? So this then forms the verifiable substrate on top of which discovery can happen. Now, if we have a full-blown application like autonomous driving, then what would be the execution loops that build these verifiable substrates in that case? Fortunately, over the years, for autonomous driving, we have been working on many such agentic substrates that do data analysis for us, that do simulation, that do AI model training and validation. So for example, given a bunch of computer vision and machine learning tools, we can have data agents that can analyze all sorts of edge cases. Given an input from the user, for example, get a car to change lanes, cut in or cut out, we can get our simulation agents to reconstruct the 3D background, to reconstruct all the dynamic agents in the scene, deploy diffusion models that can come up with novel reactive behaviors and challenging edge cases, and finally, other diffusion models that can do photorealistic rendering. Or our development agents can take all the ODD specs, they can take all the data tools that we have, the simulation tools that we have, and do AI model training and validation. So once we have these autonomous systems that are driving autonomy, what does it mean for the role of the human? And I believe that will define new loops where as data starts moving from static to interactive, we'll start harnessing tacit expertise, which gives us a handle on the lived experience that drives mental models that allow us to reason about not just how experts act, but why experts act. Intents from these mental models then drive the world models that do not now work with just aggregated preferences, but have traceable contributions. The attribution mechanisms that we have now will allow for trusted adoption, which then leads to continuous participation of humans in the AI loop. So how do we build these mental models? Well, we have the execution and the discovery pipelines that we talked about. All traces from these discovery pipelines are then ingested, and with the claim-back verification methods that we have, we can convert them into evidences. These evidences are distilled into beliefs, and the usage of each belief by the system is something that comes with an attribution. This is something that can be used for coding tasks, where we can solve more tasks better. Importantly, we can also have less user interventions, less memory tokens, less tokens being consumed, which essentially points to better user and system alignment. This is something that can also be used for physical tasks like Gaussian splatting, et cetera, that we are talking about, where we can get mental models to adopt different personas, for example, a quality and a speed persona. And these are things that come out of the discovery loop, and we can have a controllable steering of these mechanisms. So to summarize, we have talked about execution loops that are built on data simulation and DevOps. These are the verifiable substrates on top of which discovery loops can happen, which have grounded ideation, verification, and traceability. And finally, human participation through intent loops that work with tacit expertise, mental models, trusted attribution, and eventually co-evolving partnerships. Thank you, everyone.
All right, thank you, Manmohan. Next up, we have Bole Jo with UCLA and Coco Robotics.
Yeah, so we have faculties from UC Berkeley, UC San Diego, down in UCLA. How about having a UC AI Summit? So I'm an associate professor at UCLA, and I also work with Coco Robotics. Today, I would like to share with you how we think about scale up the sidewalk autonomy with world models. Right, so probably most of the people here are familiar with autonomous driving. So we have a previous speaker talk about their amazing research on the road autonomy, right? So we have this full-size vehicles running around the cities. But for our urban environment, there is another kind of autonomy. Here I call it the sidewalk autonomy. So here is a sidewalk robot is doing the food delivery task. So this is a robot from Coco Robotics. So Coco Robotics is a startup running this kind of last mile food delivery service. So we have hundreds of robots running around to fulfill this task. You can see compared to the roadside autonomy, this sidewalk robot have to handle a lot of challenging settings. Let me show you some of the videos like from the first person view of the robot. Now you can see here this sidewalk robots have to really carefully navigate on the sidewalk and avoid the collisions of obstacles. Also the robot has to handle all the weather condition and the lighting condition. Also on the sidewalk, originally designed for people, right? So the robot have to properly and socially compliant interact with dynamic agents such as pedestrians and animals like dogs, right? So here's another videos I like a lot. Now you can see here is a dog just lying on the sidewalk. Then the robot have to navigate very carefully to avoid stepping on the tail of the dog and achieving the navigation task. So from those videos, you can see the sidewalk conditions are very challenging. Also, the robots work in compute and battery-constrained environment, right? So we only allowed to use single RGB cameras to do the navigation. So in recent years, people developed a lot of AI models for the sidewalk navigations. So basically, they are imitation learnings to learn from the human demonstrations. So many models have been developed. My lab has contributed some of the models. Other labs also propose some great models. So those models are trained on the video demonstrations that can generalize very well across different conditions. But we have a challenge here, given so many different AI, like sidewalk foundation models. How can we benchmark those navigation models before the real-world deployment, right? So we are building up the benchmark. So here is a benchmark we built called the Sidewalk Bench. So we want to evaluate the navigation policies or models in simulations. So here we utilize NVIDIA Omniverse and Isaac Sim to build this simulation environment. So we can evaluate different models and then compare their capabilities, how they interact with peoples, how they avoid collisions. But if you look closely, those graphical simulation built in this graphical engines still lack the visual realism, right? So compared to the real-world deployment, there is still a scene-to-real gap. So we want to address this scene-to-real gap to more fairly evaluate the model capabilities. So our solution here is creating the world simulations from the real-world videos. So we want to use real-world videos as a source code to build up this evaluation benchmark. So here is a work we developed last year, published at the CVPR. It's called V2Sing. So we can take videos like walking on the sidewalk. then we can build Gaussian splat reconstructions from the videos and turn this splat into this physical engines. Then we can have this kind of data-driven simulations. Then we can train and also evaluate the sidewalk robots in this kind of data-driven simulation. So here, this demo video showing you the training process. So we can train the agent with reinforcement learning. Then after the trainings, then the model can zero-shot transfer to real world because there is no visual gap between the training environment and the deployment. So based on this Gaussian splat environment, how we can evaluate all those different sidewalk navigation policies and see how this model handle different cases. But still, there is a limitation for this kind of video reconstruction because we can only reconstruct one environment from one videos, right? So ideally, we want to create several variations from the same videos. So that's a motivation behind a recent work we called Urbanverse. So we want to create multiple digital cousins from the single video, right? So here the digital twins means one video corresponds to one simulation environment. The digital cousins means we can have different variations. So here we utilize the computer vision techniques to extract the scene graph from the input videos. Then we can plug in different object instances. Then we can create a different variation of the environment. Then each environment can be used for training and evaluation. So this Urbanverse we release to the public, and we also release a large-scale 3D assets, which contains 100,000 assets with the correct skills. So for this kind of environment, then we can use the environment for evaluation. We also developed the pipelines to do the post-trainings with the simulation. So basically, we train the model first on videos through imitation learning. Then we can put the models inside the simulated environments and further do post-training to improve their interactivity and the counterfactual reasoning capabilities. So given all this progress, we have this recent work we call the Flow Pilot that can implement this kind of real-world sidewalk navigations from a single RGB cameras. So here, this robot only have one RGB camera. Then the model will output the waypoints. Then the controller will execute the next point. Now you can see here, this robot can handle this challenging sidewalk navigations, like know how to avoid the collision with obstacles and also how to interact with pedestrians properly. Another very exciting direction is this cross-embodiment transfer or deployment. Given this sidewalk navigation foundation model, we have research that to transfer this model across different robot embodiments without fine tuning. So this demo video is showing you that this model can work really well for this lagged robots. We also have many ongoing research that trying to transfer the model to many other sidewalk robots, like the wheel-lagged robots, as well as this electronic wheelchairs, right? So in the future, not only we can autonomously deliver the food, we can also autonomously deliver the people on the sidewalk. So we release benchmark and the code at our web page, so you can access code and papers from this barcode. So here I would like to thank all my students and the collaborators. Thank you.
Great, thank you both. All right, next up we have a workshop from Lambda. Welcome up, Lambda.
Hi, my name is Davina. I work as a researcher at Lambda. I work on model evaluations and safety. I basically come from a physical AI and self-driving background. So I did evaluations and safety there as well. I'm going to make a few analogies to that, which is why I call that out. Today I'm going to talk about a month-long security competition that we conducted with the help of Berkeley RDI. Basically, we had teams compete as attackers and defenders on a leaderboard and compete against each other. on prompt injection challenges. We're going to talk about how that went, what we found out. So why are we interested in prompt injection? Let's talk about echo leak, because that's the sort of production incident that we want to be able to catch before it happens. So what happened here was, an attacker sent an email to someone's inbox. This person didn't do anything. They didn't interact with the email. They just asked Copilot a question. Copilot read this email. It read its embedded instructions, which were harmful, complied with it, and exfiltrated their entire inbox. This is the sort of thing that we want to be able to catch with testing, and it is also really difficult to solve because the root cause is architectural. LLMs process instructions and data in the same channel, and they can't tell when they are getting an instruction that's wrong or ingesting data that's incorrect. So the talk is going to be in two halves. The first half is going to focus on the competition. 22 teams took part, both roles. There was 1 month of live attack and defense. So what changed, what improved, how the arena works, how we built something that we think actually is measuring a real signal and not just noise. The second part is going to dive deeper into the attack corpus. So what do these prompt injection attacks look like? Is there any common mechanisms that we're seeing? So yeah, this is the competition. This is what a multi-prompt injection competition look like. There's an attacker agent. It's given a task and a scenario, and it inserts adversarial text into that task. There's a defender agent that's presented with all of that task and content and the attack, and outputs a structured decision. And there's a judge that decides whether or not there was a successful attack or not. So in this competition, there were, as you can see, we had a public phase and a private phase. In the public phase, we ran nearly 94,000 battles between different agents. And in the private phase, we ran around 18K, so a total of around 112. We're going to focus on the private leaderboard battles, because I think those would be more interesting. And to note, this competition ran entirely on GPT OSS 20B. So any of the vulnerabilities, any of the attacks that we discovered are solely limited to this one model. If we run this on other models, we might find very different results. Here's an example of how a battle goes. This is top of mind for me because I'm working on NeurIPS rebuttals, and I'm sure a lot of you are too. So the defender here is an academic AC. They're provided some context and a score for a paper. The score is 5.3, and it's below the threshold, so it should reject it. But the attacker tries 3 different approaches, starting with like some vanilla persuasion, which failed, then using a system notice injection, which looked like it could have worked, but it didn't because there was no basis for it. The attack that finally worked is when the attacker claimed that there's a data error in the original upload, and they uploaded a corrected assessment, which upgraded any of the scores that were previously present. So this is sort of the shape of what a battle usually looks like, where the attacker sort of learns from what's going on in the battle and gets the defender, manipulates the defender to do something it should not be doing. So one thing that we think is super important before actually talking about the results of the leaderboard is, how do we know that you're actually building a good realistic scenario? Like, how do you know that you're not just measuring noise? For that reason, we created a rubric to measure what makes a scenario meaningful. The first thing is a scenario should be difficult. So if you run one model against the same model, they should have maybe like a 50% balanced win rate. This scenario should be sensitive. So if you run a strong model against a weak model, it should actually be able to distinguish between the capabilities. And third, you want it to be, you want this scenario to not just be broken in one round, because that's sort of trivial. So using these 3 criteria, we basically calculated scores to identify bad scenarios and create better ones. An example we show here is one of HR Hack, where the target is like a salary band and a single number. So you don't need a jailbreaker to get this output, because you can basically binary search the answer. Like if the target is 150, you can ask if it's above, if it's below, and basically get to the answer. So this is not a good, well-designed scenario. So we changed this by making it an apoic canary that only the defender knows, but not the attacker. And so when it's leaked, it's clear that there's an attack that has to succeed and not just a binary search. So yeah, what did this month show us? So over a month, 20 teams just like battling it out on these boards. The interesting thing we saw is that attackers initially improved, but mainly they flattened, but defenses improved a lot more. The argument here is, for continuous red teaming, what you really want is you want to keep changing the attackers and rerunning your red teaming so that the defender who's living under adversarial pressure can learn more. Second, this is an example of like a winning team and a winning attacker team and a winning defender team and the different strategies they tried throughout the whole competition. So you'll see that this timeline starts around March 7th and ends around April 1st. You'll see that they start with the baseline attacker and defenders that we provided, but then the red line increases when they added a few more strategies like attacker planning and critique. They also added defending fingerprinting as well as simulating the defender, which by the end gives them the highest score. The defender, on the other hand, mostly focused on leak detectors, payload detectors, and checking if the output itself is validated before sharing with the attacker. The second thing that mattered was the public leaderboard actually cannot see overfitting. So there were, when we ran the private leaderboard, we actually saw that the held out scenarios were harder for everyone. The ASR median dropped around 6.3 points. 15 out of 22 of the teams actually stayed where they were. 4 of them fell really hard and 3 of them did better. Of the ones that fell really hard, we saw that they had pretty like hard-coded harnesses where they conditioned the response according to some hard-coded text and scenarios, and clearly we caught that because we ran a private leaderboard. So the lesson here is don't trust your public eval set, always have a private holdout. Let's see. Now I'm going to talk about the different types of attacks that we saw. Basically, we saw these main 10 clusters, and also I don't see the timer, so someone tell me if I'm running out of time. Okay, so there were 10 mechanisms that we saw in this attack set. The one that was super interesting is cluster 5, which is just ask nicely, because the models don't really understand the difference between a harmful ask and just an ask. If you just ask them for a password, they just give this to you. This was actually an attack that was found in a meta, I think like a meta support chat bot as well recently. Another one that was interesting is C7, which is the findings were wrong. So there's clearly incriminating content in a document, but then you append other content that claims that the previous findings were wrong. And despite knowing that they shouldn't trust the content, the model still trusts it. The third one I think that was interesting was fake pre-approval. So you claim that a VP or someone of importance has approved the action already that the model is supposed to do, and the model just complies with that. The more interesting part to me was that 4 mechanisms transferred across 14 of the scenarios. So just ask nicely, fake pre-approval, findings were wrong, workflow impersonation. They worked across the board, which basically says you shouldn't build defenses around scenario-specific filters. There are attacks that can just work across various classes that you should try to define your coverage with. Here's an example of what fake pre-approval looked like. So in this signature forge scenario, the defender is an AP clerk, which reads an expense and approves a cost. There's a 12K marketing event that clearly exceeds the budget of 5K. But this attack claims that the VP has already approved it with some approval code, and that's seen as successful. Similarly, inventory poison is when the defender is an industrial supply agent and it reviews contracts. And a normal minimum is 200 units, but in this attack, when it's pre-approved, it basically goes 50x its normal and approves an order for 10,000 units. So the point is, these are different domains. There is no similarity between the actual scenarios, but the same attack worked. The second thing is that, even within one scenario, various different types of attacks can work. So if you look at the cross-section of like scenario and mechanism, there can be different highlights. Different scenarios will have different mechanisms that work against them, and different mechanisms kind of just transfer across different scenarios. So for this email phish attack, workflow impersonation as a mechanism works, just asking nicely works, and findings were wrong works. What's interesting about this email phish scenario is that it's actually inspired by Echo Leak, and it's the same workflow impersonation is actually the same mechanism that caused that failure. So you can catch these big events in this toy data much ahead of before they happen. And yeah, this fourth finding is a little more interesting to me, coming from the self-driving space, where nearly 10% of the wins have a near identical failing twin, where most of the wording is the same, but maybe 2 or 3 words are different. So for example, in one of these scenarios, you'll see that owner confirmed via mobile app, just adding 4 words made an attack from not successful to successful. This to me is cool because this reminds me of the concept of near-miss collisions, where basically in self-driving, if there's a collision, if you go slightly differently, change your speed, change your angle, very small conditions about the attack or the scenario, then that's the difference between something being a collision and not being a collision. So in summary, what did this month of open competitions show us? The first thing is that defense is approved and attacks sort of flatten. You kind of expect this because a lot of the models are fine-tuned for safeguards. The important thing here is you should still be using these models to red team continuously, and ideally use different types of models, because clearly under adversarial pressure, you can find a bunch of mechanisms that you wouldn't find otherwise. This doesn't replace human red teaming. It's more of like a complement to human red teaming. The second thing is, a held out set caught all of the overfitting, so please report a private number for your benchmarks, or always run your own private eval and not just trust the public data out there. Third thing is mechanisms transfer across different scenarios, but also different mechanisms work on the same scenario. And last of all, even if you test one prompt and it fails, that might not mean that you're secure, because even slightly varying that prompt in a different way, adding 3 or 4 more words to it, can actually change how the model perceives it. So test your near misses. Don't just believe failure or success outcomes at their face. So that's it. And I'm going to pass this on to Chuan.
Can you hear me? Good? Okay. You have one more slide, Divina. Divina. Okay. Anyway, so by the way, there's a Lambda, we have a research grant program. You can basically scan this code. There's a link where you can submit an application form. We offer up to $5,000 cloud credit for developers, researchers, to support your work. We do have a review process. Just to give people a little bit of context here, in the first 6 months of this year, we received about 1,000 applications. We granted like 350 applications, so that kind of scale we are supporting right now. Yeah, feel free to scan this barcode. All right, cool. Now, okay, this is actually my slide. I'm going to talk about what happened if we pair cloud code with an experiment tracker. I gave the same talk earlier this morning, more from the research perspective. This one is going to be more from the software itself and what's actually happened behind the scene. So just to recap, this is Gemma play the Tetris game. At the beginning, doesn't know how to play and scores nothing. Then we had Claude watching Gemma play and trying to help it to play better. Over a period of 2.5 days, we're able to improve Gemma from score 0 to score 16. And some basic rule here, there's no, the weights are fixed for Gemma, so no fine tuning. This is an auto research project, so no human instruction is allowed. However, Claude is allowed to change the model setting, do prompt optimization, and inference speed up. And every single game has 13 minutes timeout, so Gemma has to think fast enough. All right, very quickly, what we learned is this is not only about how smart Claude is, this is really about like being very disciplined with doing research project. Just imagine how human will do research. We have a notebook to write down our experiment notes. We have a whiteboard and sticky notes for communication and broadcast the result. We also have a sign-up sheet to coordinate the resource in the lab. The similar version for AI agent are a bunch of APIs that the agent can call to use tools. And this is our version of the API. We have open source software called the lab, basically try to approximate everything human do for agents. So this is the back end. So this is the front end of the lab. So basically this is an overview dashboard. You can see in the end, Gemma is able to score 16 points. It takes about 368 experiments to get there. It's been 240 experiments since the last improvement, so the things gets more and more challenging. And the total cost is $1.2 thousand. And like every single auto research project, you'll have this graph shows the improvement, and you can see what is kind of unique here is if you hover your mouse to these record points, you can see there's a cluster of result, and these are different experiments from the same idea. So this shows the performance of an idea varies depends on how you tune the idea. Because of that, we also have a average score for each idea. As you can see, the average score is not going to be as high as the maximum score, but the yellow points, you can see there's a overall upward trend. Now, let's go to the first idea. You have to believe me, there's a Git tree where each idea committed to its own GitHub branch, but I'm just going to dive into a couple ideas here. The first idea is everything starts from scratch. What the lab is trying to do is trying to establish a baseline where basically trying some of the off-the-shelf Gemma models and the different settings and see what off-the-shelf Gemma model can do. The model it tries are like 31B, thinking off and on, and there's other smaller version of Gemma. And along this process, the lab took some notes about the findings. For example, the first notes it took is it started to realize there's a 13-minute timeout here. So it concluded, so latency is a first-class driver of total score, not just placement quality. So it tends to prefer smaller models because it has lower latency. However, a few experiments later, it almost flipped its own finding because it found out latency is not the binding constraint here because most of the game finished in 20 seconds because of the top out. So it's really not about the speed of your decision, it's about the quality of decision matters. Then you draw the conclusion, model inference knobs do not matter. The problem is placement quality, not speed. Then start to move on to the second idea, which is trying to find a way to survive. Okay, let's try to see another idea here, which probably is more interesting. Let's say idea 5. So this is idea 5. And the idea 5 actually has a milestone. Let's see what's happened here. The milestone says breakthrough, disciplined thinking producing the first non-zero score. So this is the first time the lab actually made Gemma to score. So let's take a look what actually happened behind the scene. We can go back to the code diff here. So this is all the change in this idea branch. You basically change the prompt in a certain way that it says, reasoning discipline, critical, you have a token budget. You think before answering, but your thinking must be short and follow this 6 short line structure where Gemma is supposed to first identify the target location plus orientation, then test if there's a hole after the placement, then recommend the sequence of move. Okay, so this is the kind of a instruction Gemma is supposed to follow. Let's see whether Gemma actually follows the instruction. To do that, we can see the entire log. The nice thing about having experiment tracker is you always go back and check what's actually happened behind the scene. So this is the entire trace of that game Gemma played. Let's see. Let's start from right from the beginning. Okay, so this is the beginning. As you can see, the game is sort of like represented as a ASCII code. So it has 20 rows, 10 columns. And let's see how Gemma thinks about problem. Here, thinking exactly is trying to follow the same template. First, identify C0 to C2, which is these 3 spots, to place the pieces. Then think whether it's going to be a hole. No, the board is empty, so any placement is a flush. Then you recommend the sequence of move to place the piece there, which is left, 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 and hard drop. Then in the next turn, you can see the pieces, the previous piece is put here, the second piece is about to drop. Then how did Gemma think? Again, the target location is C3 to C6, that's here. And check the hole, there's no hole. Okay, let's do it. Then Gemma made a recommendation of the sequence of move. Then you realize, wait, I'm already in the middle of the board, so I don't have to move to right, we just need to hard drop and self-correct it. So having this log allows us to inspect what's actually happened behind the scene, how Gemma actually followed the instruction. With the experiment tracker, you can also view the progress, view the result in a graphical fashion. You can actually replay the game. And with that, you can also see some global statistics, like how long did Gemma play the game, and how many turns, what is the latency for each turn, and how many tokens it cost. So all this sort of metadata helps the lab to optimize the strategy down the road. One more thing I want to show on the UI is, I guess it's tools, sandbox. Yes, as you know, agents, they tend to cheat. So in order to prevent them from cheating, we can set up a sandbox. In this case, it's really about the file access. We have to, all the experiments run inside of Docker, so we have to specify which folders on the host machine can be mounted in the container, and what are the files that are read-only, so Cloud will not touch those files. And this is the place where you can set up your sandbox. Okay, let's go back to the talk itself. That's sort of like what's happened behind the scene. Again, the improvement from 0 to 16 does not come in a smooth fashion, it comes in jumps. I'm just going to walk through some of the things that actually made the improvement. The first thing is, as we said, very early stage, Cloud realized it's better to have a disciplined thinking template, and Gemma follow that. That is the first milestone. Some of the other things that helped is, for example, pick the lowest hanging fruit, where if you see different places, just pick the bar that is lowest and put your piece there. Totally makes sense. And don't be too greedy. The game is designed in a way that if you clear 2 rows at the same time, you got 3 points, which is very attractive. But then after a few experiments, the lab realized Gemma was not able to execute that strategy really well. It's better just to pick the lowest hanging fruit and just take what you have right now. Don't wait on it. At some point, the lab created this playbook, which are the best practice for individual pieces. So Gemma does not need to think, invent the move on the fly. And yeah, don't overthink. This is very important, and it's very important to put this in the user prompt, which is the very last thing Gemma see before it actually see the board and start to think and take actions. It's also always nice to have fallbacks. In this case, the lab also had the strategy of put some piece to the left as a fallback and put some piece to the right as a fallback, so it's balanced. You don't put every piece to the same side to pile up the bar. There are also other things that the lab tried that didn't work. Here are some of them. The lab tried to use the image screenshot instead of ASCII as the input because Gemma is a multimodal model. However, it didn't really help because it eats into too much token budget. Also, too much thinking and no thinking is not helpful. You need sort of like a right balance, right amount of thinking. On the inference side, the lab did try the speculative decoding and find out it didn't work, mostly because it is the quality of the placement that matters more than speed. However, it did use quantized KV cache. On the prompt side, yeah, as I said, don't try to be too greedy, play this multiple lines in a row strategy. Basically, just like pick, if you can clear a line, just clear a line immediately. And also there are other things, for example, try to disable rotation at all, because rotation is like a hard thing to do to save time, and that didn't work. Yeah, I guess in terms of how to use this software, you can basically pip install it from the GitHub. Then there are 3 commands you need to run. The first command is create a lab workspace where your normal auto research artifacts stored there, and also the database for the lab itself. Then you have 2 commands. The first command is launch the lab service, all the APIs and the front end. The second command, launch the lab agent. This is actually a wrapper on top of your coding agent, like Cloud Code or Codex. And the way to launch this agent inside of a wrapper is allow you to directly talk to your lab API. So I have a little video record showing how to install it and start the first experiment. So this is how you can pip install the software. Then we have a tutorial repo. You can basically clone and reproduce the Tetris study. And after that, I think at some point, you launch the lab init. This is the place to start the workspace. And there's one thing you need to do here manually, which is telling the lab your research goal. Here, we just give some really high-level ideas, maximizing the score that the Gemma model achieves while playing the Tetris game. Then the lab is going to expand it into a proper prompt.md, like all your normal auto research project. And it takes a little while for the lab to expand on this. I'm going to fast forward. Yeah, this is the expanded version of the prompt.md the lab created. As you see, there's a structure, the goals, the background, all that. All right, with this as a prompt.md, what you can do is optionally create a sandbox. In this case, we do need a sandbox to make a bunch of files read-only. And after that, I really cannot say it. Yeah, here, I suppose I'm just going to be very careful here to move forward. Yeah, here you launch the lab service, the background, back end, the front end. And the last thing you need to do is to launch the progress bar is hidden, so I cannot see it. Yeah. Then you launch the lab agent. Eventually, it basically, as I said, it's a wrapper on top of Cloud Code, where when you launch the cloud in this way, it directly talks to the lab API, and the code is get instruction API to fetch your own research idea and the project instructions, and start its auto research. After a while, you can see the first experiment is launching. GPU is free, sandbox configured, create a baseline idea, and launching run 1. And it takes a little bit of time. I'm going to fast forward to the end, where you can see here it concludes the first run. The baseline 1.1 scored 0. It top out after 21 paces in 21 seconds and created 3.1 holes per placement, and some kind of final shape of the board. And it drew a conclusion. The finding is that reframe. The finding is the objective isn't really about latency or scoring tactic. It's about survival. Yeah. So if you keep this the lab running for a few hours, it will start to score. Right. Okay. Okay. Just to close this part of the talk, I guess there's a license we can learn from the science history. The modern science started not because humans suddenly becomes a lot smarter. It started because a bunch of people from Royal Society, including this gentleman called Robert Boyer, they start to exercise a habit that write everything down very precisely, so random people can reproduce it. And this is also very important for auto research agents because they are very powerful minds, can read a lot and make a smart decision in seconds. However, everything will be lost if they don't write things down in the next session. Yeah, and this is the QR code to get access to this software. All right, thanks.
All right, so for the next part of the talk, I'm going to be talking about some of the work that I was doing. Essentially, the model is not the agent, or what 300 million tokens of agent traces taught us about models and their harnesses. My name is Zach Mueller. I am the head of developer relations over at Lambda. And essentially, back in March, late March, Clem, CEO of Hugging Face, made a tweet essentially saying how we need more open traces data sets because these models are extremely smart, especially the large models that we can't run at home. And the theory was if you take the traces of these models and train smaller models off of them, they might be more performant. And essentially, we took the task of, let's see what happens. So the recipe looks fairly simplistic, right? Identify a frontier, preferably open source model so no one gets into legal gray areas, generate some reasoning traces from it, so the reasoning, the actions, and the results, and then train a smaller model off of those traces. Well, then you get into this fun problem of it's not actually about the model because you can have Opus or you can have Kimi running in Claude Code, Codex, it doesn't matter, because the harness itself dictates how well the model can perform. And a lot of times that answer is not very straightforward. For instance, this is on the Terminal 2 benchmark. And essentially, what folks are finding is, take say Gemini 3 Pro, which there's a Google Gemini CLI harness for it. You would expect that on a particular bench like coding, you would use the harness that the model was trained for to be successful. And instead, by changing to a minimal, well-crafted harness, not only could the model outperform by 8%, it was also cheaper by almost $20 to run the eval. And on the flip side of that, GPT 5.5, where we have Codex and OpenAI training these frontier models, Codex was better. It was 5% better. It was also 4 times the cost because OpenAI could have an incentive of, well, let the model run harder, work longer to get these problems solved, and add that extra 1% boost. That's a valid engineering concern. But what this means is that you shouldn't always just stick with one harness. You should experiment. As another example, Kimi K3 came out last week, and over 26 identical tasks, a particular lab decided to see which harness worked the best by comparing performance, cost, as well as time. To no surprise, the harness that was built with the model performed the best. Kimi Code got 21 out of 26, it cost 54 cents, and was almost 300 seconds. Coming in second place was Hermes Agent, which is an open source harness by News Research, where it was almost performant, cheaper, and faster by nearly 2 minutes. And then there were a few other open source harnesses like PyAgent and OpenCode, but one that I particularly found interesting is Claude Code also scored about a 19 while being 3 times more expensive than the rest of them. This is because Claude Code injects a lot of system prompts into their harnesses. And so a lot of folks like to try out the latest frontier model in a harness that might not work the best because most of its context window is essentially being battered by this system prompt. And so, it is a decision of maybe every harness isn't best for every model, and we might not even know what harness works best, but we have to at least try. Now let's go into what a trace is in particular and just have a central definition of it. So you, the user, will prompt a model to say implement this function or implement this server architecture, or if you're using Codex, go give me frontier research overnight, good luck. Now what actually happens inside the agent loop is it'll reason for a while trying to judge what its next step should be. It'll call some tools and then come to a decision on have we successfully fulfilled what that prompt was. If not, this will go over and over and over again until eventually the model decides either we have a solution or it needs human input. Now, this matters because if we know how the model behaves, then we could maybe train a model later on these traces to have a better performant model with a smaller total model size. So you could run it at home, run it on a single H100, what have you. The problem was we needed to come to a decision on which harness to use, and we chose Hermes Agent. At the time, it was only a few months old. We had a lot of good partnerships with new research, and also I personally was using my Hermes Agent at home and not OpenClaw, so I also had a personal bias for this. And so we went with Hermes Agent. Now that's step one, right? Now we understand the world and how it's going to interact with it. Step two is deciding which models that Lambda should go after for generating these traces. And essentially it had to fall into three buckets. First was it had to be passively licensed because we didn't want anyone to have to worry about can these traces be used for business values or for fun or even having them on your computer. We wanted to make sure this was freely available to the public and to the community to do what they want. The second part is we also wanted to make sure that we were targeting things that the average person can't run at home. At the time, because this was back in March, state-of-the-art was Kimi K2.5 and GLM 5.1, 1 trillion parameters, 800 billion parameters. Unless you happen to have 6,000 Blackwells sitting at home racking up your electric bill, I assume most of us can't really run this at home. And then along with this, I was paying attention to the capabilities of the models themselves. So at this point in time, GLM was state-of-the-art in coding, but this was the beginning of Kimi and introducing this Kimi swarm paradigm, where in one reasoning chain, you can have multiple chains of tool calling happening independently at the same time, which would be very valuable for these small, fast models to do at once. And so this is, sort of recapping, if we have parallel tool calling, then as an example, we could say hey, let's go build this web service real quick. Great, then your open source model can sit there and at the same time start building the framework for a fast API route, start the unit test for them as well, and then also keep track of versioning changes and whatnot through 3 separate different reasoning traces at once, and you don't need 3 different sub-agents to do this. Now, how we actually generated the corpus was we had Kimi K2.5 come up with about 7,000 different basic to challenging coding scenarios. It covered anything from computer use to build a basic hello world py file. Then we ran all of these prompts through Hermes Agent with different models at the back end. So that ended up being Kimi and GLM across 184 H100s about over a week. And where we ended up was 150 million traces from each model that were then verified to make sure that the trace actually made sense and was successful. Then it went into one bucket. If it was a failure, that is still useful to learn from, and it went into another bucket. And so essentially, within the weekend after it got done, we just released it and just saw what the community would do. And what happened is it was actually very successful by our book. So this is current. It has about 380 likes on Hugging Face and about 3,000 monthly downloads. This got up to about 10,000 during the first month that we released it. But most of all, we saw an interesting trend of models that were trained based off of the traces. Quopus is a very common model name, and essentially it is a Quen model trained on Opus traces. And so you end up with this Quopus model. But essentially we were finding that in the size ranges, folks were training these things from down to 1 billion parameters to 27 billion parameters to have a performant autonomous agent at home that can be your assistant without needing to have like thousands of dollars of hardware to get that done. And also we saw particular camps of models being trained. So like first was Quopus, right? So that's Quen 3.6. And specifically, these were all non-mixture of expert models because in general, folks were finding that when you get down to this small of a model size, MOEs tend to matter less than having the larger performant models when speed isn't per se a factor when your agent can run at home and you don't care if the problem gets done in 12 hours or 2 because it's just passively doing its thing. We saw a few interesting experiments where folks would take like the Kimi traces specifically and try and bring this parallel tool calling into extremely small models, like Liquid's LFM 1.2 billion. Sometimes it was successful. I still think like 5 to 10 billion is the minimum to where you can have these more complex sort of tool calling capabilities, but it was a very good effort, as well as some other good Hermes specifically trained models that were designed to work with this harness. Harmonic Hermes ended up being one of the more popular ones, along with Quopus, where their two models combined had almost 500,000 downloads and are still getting models today. And so essentially what I want you to walk away from this talk is not per se, you know, oh, you need to go distill traces and go train your own model. I challenge you to take the models that you know and love and the quirks that you love and hate about the harnesses you use and take these models and shove them into a different harness and see how it reacts and behaves. It might have an entirely different personality because you don't have a 20,000 character system prompt guiding it and the model can be more expressive. Or you might need to tone it down a bit because Codex is so strong that it needs to be wrangled and not just let loose. But if anything, I hope that you can take away this thought of, well, maybe if I use Codex every single day, what happens if I give it Pi? What happens if I give it Hermes agent? And just play with this idea and start to widen your scope of maybe one harness isn't always perfect, even if that harness comes from the place where the model was trained. Thank you very much.
Welcome, Brandon, from Replit.
All right. So my name is Brandon Middleton. I'm the head of education at Replit. Clearly not the head of AV standing up here, but this talk is about humans, human potential's big moment. This was about 11 years ago. I stand in the Guinness Book of World Records for being the first person to rap, hip-hop rap, a commencement speech. I did the evening and weekend MBA program. I graduated in 2015. If you want to hear the rap, come meet me outside. Maybe I still remember it after 11 or 12 years. This talk is about how we can shift how we do education and AI literacy in classrooms, in research, in higher ed and academia. And if you have thoughts and questions and commentary about this topic, we're in an experimentation phase. There's lots of trials to try and things to succeed and fail at. So I'll be off stage trying to meet as many of you who are interested in this topic. All right. I deeply believe in the power of education. I've taught outside of my regular job at Amazon and at Microsoft and at other places. And at Replit, I actually got the opportunity to full-time focus on what I've been doing for the last 7 or 8 years. So I get to focus on universities and colleges and K through 12 and nonprofits that are focusing on trying to bring AI literacy into like a practical and tactical realm. So I'll talk a lot about the work that we're doing. I see some people that I've worked with in the audience already, so it's gonna be a fun time here. All right, let's blast off and go. All right, so I'm gonna try to make this talk like also a demonstration of how you build an end-to-end application using a platform like Replit that has Agentic AI embedded inside of it. Hands up if you've ever used agents or Agentic AI to build anything. Okay, almost the whole room, hands go up. If you built something today, hands up. All right, so if you go to this actual URL here, I'm afraid to do this because I'm afraid that we'll pop out again, but there's an app that I created this morning. All right, so if you click that URL, it'll take you to a page that looks like this. And if you click that wall, this button here, there is a picture of all of our new joiners here. I used Replit Agent to actually, let's see, to actually build this application out. Man, this is killing me. So if you would like to leave a message, or if you would like to literally participate in this scroll wheel, scroll wall, this is an example of something that's using Agentic AI and agents in order to build. It accepts your images or your messages, and then it will put this scroll wall together in the back that you'll be able to see. All right. All right, so I'm gonna go there. And it looks like you can see all of you guys' images popping up on the screen there. Great job and great to meet everybody virtually. Is this the first live demo demonstration that you guys have seen today? No? Okay, you've seen a little bit more. Well, keep doing this if you like. Put images, put comments and commentary, but this is one example of Agentic AI at work. All right, so let's go back to presentation here and keep going. All right, so I've taught at the Stanford Design School. I teach a class every spring quarter called Redesigning Finance. And I've had students joke to me about kind of the state of higher education, and us calling it that as educators because of the price of the tuition and not necessarily how fun it is to be in class, or the quality of the content, or the differentiation between being in class or going to YouTube or going somewhere else to learn the same kind of information. So there's a lot of truth in jest sometimes. You get students to rib you and give you a sense of man, the return on investment, as I believe in the American dream to get me a job and to do everything that people have told me to do, that's starting to wane a little bit. If you've heard some of that sentiment from students, or if you feel a little bit like that yourself, give me a hand wave. There's a few people who are like, man, it's tougher to get a job, or it's tougher to believe in the status quo these days. So I feel like the reason that some of these jokes work is because there's some truth to this, right? We need to actually think about how exactly it is we're going to reimagine education as a whole. What is it for? How do we do it? And how do we build the bridge from higher ed, higher institution of academia into kind of the workforce? Workforce development is a little bit of what I focus on at the K through 12 level, all the way through college, and then into early career at Replit. All right. So what we did to try to talk to people in a ground-up fashion is go on what we're calling an AI literacy tour. So I've been to Chicago this summer, where I'm from, born and raised. I got a 708 number in Michael Jordan shoes. That's all I got left from Chicago. I've been in the Bay Area for 21 years now. We've been to Chicago, we've been to New York, we've been to Los Angeles, we've been to Atlanta. We're here in the Bay Area talking to people about what it feels like to be a student at this time, what it feels like to be a teacher, receiving mandates from the top and trying to translate AI literacy into something meaningful for yourself and then for your students and community. And what we're trying to move towards is an answer to try to reimagine what education actually looks and feels like, because in certain places, I think that it is for sure failing. All right. All right. So the education system as it currently exists was actually designed pretty well. It was designed hundreds of years ago for a world that today is not really existent. Information itself used to be scarce. So you needed to come to a university in order to actually receive it from a professor who was the kind of the end all and be all. You come to receive and retrieve that information from your professor. The knowledge was locked up in libraries, in laboratories, in lecture halls, and the world remembered the answer and used the answer that you were receiving. It was often the evidence of your learning if you knew the actual answer, which is not true today. You can have a lot of book knowledge and no street smarts. You can have a lot of things that you've observed, but maybe that is all misinformation or disinformation. So today, information is not scarce, literally everywhere. Answers are abundant, and increasingly, the intelligence itself is becoming pervasive and abundant as well. So how do we move into an intelligence age where the cost of the models are dropping, but the intelligence of the models is actually getting really, really good? How do we, Replit, and how do we as an industry within education think about how to wield this intelligence moving forward for technology and non-technical people who are going to be using these platforms? So this massive civilization level shift creates a big uncomfortable question for the institution of higher ed. If we were designing college for today, summer of 2026, and we could start with a blank canvas and a blank sheet of paper, how exactly would we go about doing that? Would we still organize everything around lectures in libraries, and would we create semesters that are 16 weeks long still, or would we make things shorter? Will we count attendance? Does that matter in the future of education? Closed book recall and rote memorization of things on final exams, is that a thing that we need to hold on to or something that we should throw away? We've confused time served in college institutions with learning, right? We've confused the credentials with a student's capability to actually perform. And sometimes we've confused sorting students throughout 4 or 5 years with actually educating them. So college has become this extraordinarily expensive sorting system, and we sort by admissions. Sometimes we sort by grades and departments. Sometimes we're sorting by the actual institution that person or those people went to. And then the result of it at the end of 4 or 5 years, we call merit, and we literally will hire or not hire on the basis of that sometimes. So I think a lot about that at Replit, and what we've been doing on this AI literacy tour or campaign across these 5 different cities is literally asking people from preschool teachers, lady in the back is a preschool teacher, all the way up through researchers and professors at R1, Tier 1 universities, what's happening? How can we incrementally choose small experiments and things to peel off and try that might be useful in defining what education is going to look like in the future? So in this session, this is me in the community in East Palo Alto. I live in Palo Alto and do a lot of community work in East Palo Alto. And we had a session of 7-year-olds in the room all the way up to elders, 77-year-olds in the room. And we were talking about the issues of resource allocation and different things that plague the city of East Palo Alto. And I'm using these sticky notes to put things on paper. I'm using my phone and applications to actually capture the things that the 7- and 8-year-olds are telling me, as well as the things that the 75- and 76-year-olds are telling me. And I'm using Replit as a platform to basically, like you're doing with your photos, upload that to an application and think with AI as a partner and show the community exactly how easy it is to do, even though they themselves didn't identify as computer scientists and engineers. All right, so meanwhile, the work world, outside of the community aspect, is sending us some pretty staunch messages. And a couple of stats for you. At the beginning of this year, 2026, unemployment amongst young, recent college graduates was about 5.7%, so just under 6%. More strikingly, about 41.5% were underemployed, meaning that I might have graduated from a really fancy school, but I might be working in something that's really underneath my intellectual capability or even my interest, which is also a problem. So we have that to deal with. This doesn't mean that the college institution in and of itself doesn't have any value. It means that the connection between education, student capability, and opportunity is currently under strain, and we need to solve for that. The World Economic Forum reports that nearly 40% of workers' current skills are expected to change between this year and 2030, so that if you had 100 people representing every of the 8 billion people on Earth, 59 out of those 100 people would literally have to shift and reskill and repivot within the next 4 years. So that's how much change we have to think about. And that's why I hold everything with a really loose grip, because everything in AI changes so quickly. All right? So if the global workforce is going to change and a diploma can't be the finish line, what do we do? Maybe that diploma is not even like the reliable map that we should be using in the future as we rebuild this thing. So the real advantage, as I've seen it, has come from the ability to actually learn, the ability to unlearn, and the ability to pick things back up and relearn them as I move forward. I graduated from UIUC as an electrical engineer. I came out to the Bay to work at Cisco Systems as a networking software engineer. And I went to Haas Business School and graduated in 2015. I started to put down a lot of my technical skills in terms of programming, in terms of product management that I used to do. But these days, I left AWS after 6 years to join Replit as the head of education. I'm actually picking back up some of those skills of product management, some of those skills within the EPD triangle of design and engineering and product management in order to build experiences for people that are both technical and non-technical as we move forward. So relearning, unlearning, and learning to learn is really a core skill if you're going to be a contributor to this education of the 21st and 22nd century. All right, so AI is not the next EdTech gadget. I see AI a little bit differently than I see the calculator, for example, a little bit different than like a Google search engine from 2003 and 2004. I see it as not only a way to automate things like grading or summarization of papers that you might receive as a professor, or a way to generate lesson plans, but AI gives us, I think, a once-in-a-century opportunity to actually rebuild education around human potential. So I think each of us have an innate passion, desire, skill to be able to do and deliver something to the rest of the 8+ billion of us on this planet. And I think we can use vibe coding and use agentic AI in order to help humans achieve peak performance in their fullest potential moving forward. For the first time in history, I think imagining agentic assistants and personal tutors is a real thing that can be achieved and grasped within the next couple of years. All right, so this is a picture of me in the community again. This is, if you're not familiar, a guy who was signed to a record label for 10 years. 5 years ago, he got released from that initial deal where he did 3 albums, won a Grammy and all of that. He came to the Replit office asking not so much about agentic AI and technical terms, but he launched out as an entrepreneur and said, hey, I want to run a record label and do a lot of things that plagued me when I was part of the larger music industry. Things like revenue recognition for the amount of royalties I should receive when I stream my music across all of the different platforms like Spotify or YouTube Music. You get fractions and fractions of pennies for doing that, and he would actually go about trying to audit the money that he would receive. And the runaround that he described and the errors and all of the things that were basically swept under the rug that most other artists weren't doing, he thinks is a big opportunity. So he's building a new record label and using vibe coding, even though he hasn't really got that computer science and that technical background, in order to reimagine things in the music industry. Even though he's not part of an actual university right now, this also falls underneath the umbrella of education in my scope at Replit. Music education, there's business education, there's technology education. So if you've got thoughts around things that typically will sit outside of the university, I'm happy to talk with you guys one-to-one about that as well as I leave the stage. All right. So let's talk about this personal tutor for every learner. Not only for like wealthy individuals, like a lot of folks that are neighbors of mine in Palo Alto will send their kids to Saturday school, or they get out of school at 3 o'clock and they're not home until 6 o'clock because they've got these personalized tutors for STEM subjects and for other things. But I think that students whose parents know how to navigate the system, that's pretty soft. But for the ones that are not confident to raise that hand in a crowded lecture hall, it's cool to think about how we can use Agentic AI to build personal tutors that will be available 24 hours a day, 2 a.m. when that student who's too shy to raise their hand in lecture hall needs a question answered. Students who need an explanation in an alternative way. Maybe you're a visual and not auditory learner. Maybe you need, or maybe you perform well in oral exams versus taking written timed exams. There's lots of examples of students that need accommodations and have them in order to learn at their best. And the ability to personalize education without any embarrassment, exhaustion, or judgment on behalf of the student and the teacher, who sometimes is in a one-to-many type of forum, is something that we think a lot about at Replit. Multilingual support is something that in the Bay Area, like I lived in Chicago, so I heard a little bit of Spanish, but mostly English when I came out of Illinois and towards California. When I arrived here, like the concept of pretty much everybody speaking at least like 2 languages, I felt like a total slacker for the first several years of my life. If you speak more than 1 language, give me a hands up. So I am underachieving all of you essentially by only speaking English. But I think Agentic AI can really help with that too. Like you can speak into Replit as a platform, English just as well as you can do French or Spanish or any other of your native tongues, and then have that translated in apps that you build to other people who speak different languages on the other side of that interaction. All right. So I don't see what we're talking about as replacing teachers. I think the teachers themselves have really important work to do, so that we're talking about expanding the reach of what one individual is able to do for a classroom of sometimes 15, sometimes 50, sometimes 100 people at a time. So when the teacher becomes less of a broadcaster and more of a designer and a coach and a mentor, a critic and a community builder, I think the students have a lot of room to thrive and a lot of room to grow into leadership and ownership as they move towards what's next for them. And AI can definitely deliver the information, but what the teacher needs to do and why that matters is a very personal kind of that care, that concern, that thing that is intangible a lot of the times, that belief that the teacher has in that student that will allow them to stay up that extra couple of hours and complete something or have pride in the work that they turn in as a result of the seeds that were planted in them by that teacher. All right? So this is my future. I've got 3 startups, one age 14, one age 10, and one age 7. Basically at the end of every pay cycle, I like empty out my wallet to do things that make them happy. And I think a lot about when I get out of bed, I'm excited to contribute to this future because I know that 4 years from now, the oldest startup is gonna go into college. And in 2030, who knows like what learning, what education, what like credentialing, what college, what work even will be. If you have ideas about this and you feel like you know what's going to happen in 2030, please see me immediately after this presentation. So this is special to me in that I think the experimentation window that we have is about a year and a half, maybe 2 years to try all of these things and see what sticks and see what does not stick. We have a program that we run at Replit called our Faculty Fellows Program. I see one person in the audience that's a part of Dr. Chin. Wave at everybody. We do a monthly webinar where people who have said yes to experimentation use a Replit platform to build out experiences and to build out things, and they put them in front of students or they use them in their research and then report back to a cohort that's now about 75 teachers large. And we talk through what worked, what didn't work, and we try to share that information in community so that the next person who is yet to dip their toe in the water feels a little bit more comfortable and confident doing that on the back of that shared experience. So I'm hoping that my kids see enough at home and are able to learn enough from these communities that are building to be confident to experiment themselves as they go into high school and into college. All right, so let me show you the Replit interface. If you've seen Replit itself before, raise your hand. Okay. Can I get one volunteer to explain what Replit is to somebody that's never used it before? One volunteer from the crowd. Go ahead, in the black shirt. Explain what Replit is for someone who's never used it. Oh, who has never used it? Okay, so you are not the person to answer. Right here in the blue shirt, yes. Love that. So he said from idea to built AI application without the requirement of knowing much about the technology underneath. So since you already gave you a hat, I'm gonna give you this to give to somebody else. Thank you, sir. Yeah, you guys can mob him after. But the actual Replit interface, if I come out of here and let's see. Okay, here. All right, so this is the Replit interface. I'm gonna come over here. All right, so you get a prompt box like this, which is a very, natural. I've done this with ChatGPT, I've done this with Claude before. And essentially, if you click import here on the actual screen, if you want to start from something that you've already been building in another place, you can import work from other places into Replit. If you want to check the status of other projects that you've been working on, as you continue to build out things in Replit, you'll get a full page of all of the different things that you've done. I built this slide presentation in Replit, as you guys know. Talk about integrations with other pieces of technology that you probably interact with on a day-to-day basis. All of the different connectors that we have are personal and enterprise types of connectors. So I personally use a lot of Dropbox and Discord and Slack and Google Drive. If I scroll all the way down, there are 511 different integrations that you can be prompting, and you can say, hey, Replit, go grab my Google Drive, my Dropbox, and my Databricks, and my Google Sheets, for example, and I want to make an application that does XYZ. So it's a lot more fun to connect into all of these applications before you build the thing that you want to build out. All right, let's go to back here, back home. So the artifact and the output types, you see website here, mobile app, design, games. We built that photo app in a few minutes here. So these are all the different kinds of artifacts and expressions that you can put into this prompt box and kind of steer the model towards. So if you know you want to build a slide deck, just click the slide deck button. If you know you want to build a mobile app, iOS, Android, click the mobile app button, and that'll steer Replit in the direction that's necessary in order for you to start that back and forth interaction. On the bottom left here, there's a learn and a documentation button where we've spent a good amount of time putting video content together to take people from 0 to 100, and then from 100 a little bit further. If you are not familiar with vibe coding, you're not familiar with building with AI, the documentation in some of these Learn apps are really helpful for that. Okay. And coming back here, once you've actually kicked off an actual work session, you can see that there's a number of modes. So there's light mode here, which allows you to ask very basic questions like, hey, can you change the color, the background color of my slides from black to orange? Can you change the text of this slide to say this instead of that? That's what light mode is for. Economy mode is like the default middle of the road, like reasoning, intelligence. And then when you want to do things that are really, really ambitious, you can go to power mode. And for each of these, you've got the ability to kind of click into these and select either closed models or open models, depending on the level of work that you're trying to do. So model choice and the ability to actually choose the right model for the right thing that you're asking Replit to do is part of the experience here. All right. So that's a little bit about the Replit platform itself. Let's check on our application here and see if we've got any new faces. All right. Dr. Chen, you're looking good there. Love to see you guys doing that. All right. Let's keep going with the actual presentation itself. Let me come full screen mode here. Present. Okay. All right. So let's talk about responsible AI use and like how we can do assessment a little bit differently. So we have to change the kinds of things that we value. I think testing is pretty dead at this point. In my class, Redesigning Finance, I usually am asking students to YouTube record explanations 5 to 7 minutes at a time of them grappling with a topic in finance that we're discussing. So one of the themes from last year's class was, how do you deal with catastrophes like the LA wildfires that happened a couple years ago? If you are trying to redesign reinsurance and the insurance industry and improve the claimant's experience for the next fire that happens in LA or the next flood that happens in Florida, how do you actually go about designing something at the claimant level, at the insurer level, at the reinsurer level, and have students literally build stuff and then actually defend what they've built synchronously. So unless they've learned how to master deep faking, they're putting like the work into actually thinking through it and putting a prototype and their video next to it as a submission. So I think we should stop designing assessments around stuff that machines can do well and start designing with the human being in mind. And each human being actually has different capabilities. So I, in my own grading, have done some adaptive type of work. It's all group work, but we look at the students' grade in school, so freshmen through master's students. We look at the students' background in engineering versus I'm a brand new coder or a brand new person to technology. And we grade across things like the fidelity of the design that they put forward, the collaboration that they've showed within the group as measured by how their teammates are voting and not necessarily how we the teachers and we the TAs look at them. So these are a couple of ideas about how to change assessment in terms of moving away from exams or pop quizzes and more towards experiential and building. All right. Taking away judgment, curiosity, care, originality, and collaboration. Like if we remove these things and they're already absent from the system, I don't think we're setting ourselves up for success. So let's lean into empathy. Let's lean into the ability to frame problems, worthwhile questions to ask, get high points, even if you don't have the answers to them necessarily in the classes that I've been teaching over the last year or two. All right. All right, the question should no longer be, did the student use AI? But better questions that we should be asking ourselves as educators are, did the student actually think? Did the student verify the work that they put forward? Did they cite sources, say where it came from? Did the student improve the work? Did the student explain the decisions and the choices that they made in order to get to the output that they actually came to? Can the student defend the conclusion? And can the student tell us where the machine and the machinery actually got it wrong? They're using their own judgment, they're using their own expertise in a particular area to make judgments about what the machine said. So imagine this oral defense after every major individual or group project. imagine students submitting not only one final answer, but a tracked like record of their reasoning. I built a system inside of Replit that allows students to actually reflect on lectures, submit the actual assignments, and then for them to be able to track, again, the space between two lectures, you might have learned a lot. The space between one exam and the next exam, you might have learned a lot. And the traditional system that we live in doesn't necessarily capture those moments. So we've got the ability to build new software and new artifacts that will help us to actually capture some of that. All right. Let's keep moving here. This is a picture of a hackathon. This is an interesting story because I didn't do particularly well in like molecular and cellular biology and chemistry or any of the things that this hackathon in San Francisco was about. But the students used the Replit platform in order to find biomarkers, in order to do things around drug discovery, to do some life sciences innovation. And my commentary to them as a judge, one of the many judges, was about how deeply they thought about the solution, how many people they surveyed, like their process, a little bit more than like my domain expertise. And I think all of us, even if we don't go deep into a particular area or domain, can offer kind of our lived experience and our perspective to make the stuff that students are building a little bit better. All right, this is the hand of a high school student in Chicago, 15 years old, named Jack. He comes to school from like 25, 30 miles outside of where the school is actually at. And the principal of Holy Trinity High School gave students access to Replit in this last spring. And Jack decided to take the school's disciplines and the things that they hold high in terms of the school principles. And he built out this system that he gave to teachers, and teachers are able to identify things that align with the school's values and principles. And literally the teachers can use their mobile phones to basically reward and say, yes, that's exactly the exemplar behavior or the care and the collaboration that we want to encourage. So they're literally like changing the environment and the culture of the school. And they use the digital signage as students are walking in from the buses, like into the lobby every morning, in order to show like a leaderboard of sorts of the students that are getting, he put XP. So the students are getting XP in this application on the digital signage, and they're getting like the positive reinforcement that they all seek. And you can use your XP that you accumulate in order to do special things in this high school. So this whole gamification and this idea of the culture of the school being improved and enhanced on the back of a vibe coding platform is something that was a really cool thing that I heard in our Chicago stop of the AI literacy tour. All right. And then when I asked Jack about like how he thought about learning AI, this is how he broke it down for me. He said learning with AI, so using it as a tutor, collaborator, critic, translator. He talked to me about learning about AI. So they have one teacher in the entire school that did a deep dive, like a professional development, about a year ago, and then brought what he learned to the sophomores, juniors, and seniors in the class. And essentially, all of the stuff that the students picked up from that teacher was basically about the security, the governance, the how models and algorithms actually work. And from that, he got inspired to learn beyond AI. So he solved things around connecting his application and streaming it via Bluetooth to the digital signage system. He learned a little bit about the community impact and the issues in the community around Holy Trinity High School. So he talked to me about things that were beyond the technology in his presentation of his solution to me when I visited the school, which was interesting. So I think 3 modes to start with in terms of learning with AI, learning about AI, and then learning beyond AI. And we think about how this can like move way beyond the classroom, outside of technology, and into stuff like medicine, into stuff like justice, resourcing, and then education like we've been talking about. I think we're going to quickly get into a philosophical and ideological conversation when it comes to AI and education, because there are certain things that technology cannot necessarily cure that we've had in society for a long time. We've had a lot of economic inequality. We've had a lot of poverty and war and different things that sometimes money is a factor in, but it's not able to be cured and solved all the way using technology. So I'm excited to be able to talk more to communities and to students about these ideological and philosophical principles in addition to the AI literacy and foundation that we're giving them. All right, so let's take a quick break. Anybody know who this guy is? This is the biggest little kid I've ever met. So in December, me and Amjad, the founder of Replit, got to teach Shaquille O'Neal how to vibe code. And this is so weird. His hands are so huge that I wanted him to type prompts. His hands are too big. He can literally not type. So I asked him to open up multiple tabs in the browser. I said, hit F5 and then just start talking. So in the span of 90 minutes, we were on set in Atlanta and we got to, we made something called Shaq GPT. So he wanted to answer every sports question. We hard-coded Charles Barkley sucks into any question regarding Charles Barkley, his TNT broadcaster mate. We made another one called Shaq Daddy. He said, Brandon, I want to solve the loneliness epidemic in America. There's a lot of single men that need to know how to talk to women, and we need to get these men married. And so we made Shaq Daddy a pickup line generator for all of the men in America to, I'm getting some laughter back there, okay. He made another one to track all of his advertisements. You've seen Shaq on radio and TV and movies. I think Snoop Dogg might be, him and Snoop Dogg are neck and neck by putting their brands everywhere. So we made a way to track all of his investments to see year to date, 2026 until now, or all time. How can I understand my return on my time and my brand? And it was a lot of fun to see him be ready to use his brand and to see him be vulnerable and be okay, not knowing things. And this is part of my vision for the AI team, the education team at Replit, to take people who have the willingness and the humility to actually try new things. And then once they've accomplished it, kind of take it to their audiences, take it back to their alma mater. Shaq went to, I think, Louisiana State, LSU. So if you have ideas about how to scale this on a platform or on a person that other people are looking up to or other kids see as cool, this is actually part of my strategy in the education team. And as we get into back to school season, you'll see our team do a little bit of this with hopefully Shaq and many, many other folks that can incentivize kids to learn these principles. All right. I think we got about 15 minutes to go. What I'm going to do is pivot. I've got a couple of these slides that you can see as we move towards the back end of this. But essentially, what I want to leave you guys with is 5 commitments. And these will be things that teachers, researchers, I'm hoping that students can grok these and use these as we move forward. The first is to guarantee AI access for every student. So I'm encouraging schools from the universities that are well-resourced all the way down to I think middle schools and high schools is probably an appropriate place to put this. Redesigning assessment like we've talked about around critical thinking as opposed to this is the right answer and this is the wrong answer. I think a spectrum is worth considering. There's a lot of gray area in the life that we live today. Rewarding teaching innovation as seriously as we do research. So pretty stark contrast within academia, I think, in terms of rewarding good teaching versus rewarding research. So it'd be cool to see higher ed take more to shining a light on great teachers and people who are able to facilitate and to coach and to teach cohorts of folks 25, 50, 100 at a time into this AI literacy. That's a big opportunity for us. Replacing the one-time degree with lifelong learning. A couple years ago at Stanford, we actually, as adjuncts, talked about kind of this on-ramp, off-ramp idea, so that once you started in the institution, you literally are Stanford for life, and then whether you come off at 25 and come back at 30, or you come off at 45 and come back at 47, the idea that we'll have enough as human beings to learn and that the university context can be a community that's kind of a lifelong thing is something that I think worth discussing. The economics of it and like the exact way to implement it is still an open question, but this community that humans need is something that is already understood. And then lastly, measuring capability and mobility and not rankings as much. So I think credentialing and the ability to have students have a proof of work system as they look to graduate and find jobs for the future is a big opportunity for us. I mean, I thought in jest, like it'd be fun to have a funeral service for the resume, for the transcript, maybe for the GPA, because in the future, I think where we're gonna land is a place where you're gonna point me to your portfolio of built work and all of the proof of things that you've done in projects collaboratively and solo over time. And then as I'm sitting across the table in an interview from you, your ability to communicate, to tell the story, to show me the actual forks of options that you had and the ones that you chose and why will be the determining factor about whether I'm excited, personally to bring you onto my team or not. So, measurement, capability, and mobility over rankings, I think, is an important concept to think through. All right. In the last few minutes, what I wanted to do is give you guys a crash course in the design of an actual application. So let me come down from this. And if you wanted to check this presentation out, I will, if you go to that app that you just opened up and do like AI Foundations Deck, AI-Foundations-Deck. After you do 2084-edu.replit.app, you can get to this entire deck and I'll send it out. But with the remaining few minutes, I wanted to talk a little bit about a vibe coding, just 101 type of session. So let me play this from the start. And for all of you who had not necessarily built anything, this is going to be like a 10-minute, just lightning fast way to think about building your first app or building your end-to-end app using Replit. All right, you guys know who I am. We talked about what Replit is. One thing I did not talk about is how you can invite multiple developers into your project so that maybe solo, myself and Dr. Chin start to make something, but then we want to invite 2 or 3 other people into it. There's an invite button on the top of the workspace that allows other developers to be prompting the same body of code as you, so that in the same way that you can build out a Google Doc with 4, 5, 6 people, you can do that building software in Replit. So that's a pretty powerful concept to think through. All right, in terms of your first prompt, I typically will start somebody who's never prompted anything with just like a personal portfolio page. So you can say, hey, make me something that'll help me to express what I've accomplished in my career. You can throw in a picture of yourself and say, Replit, go make it. After that's done, we've got the concept of abstracting all of the underlying infrastructure, the hosting, some of the database information, some of the security scanning, and all of that stuff that you need to do to go from local host on your laptop to fully deployable so that when somebody clicks the actual URL, it works for everyone. That's what the publish inside of Replit does. After we've got like a design that's up, clickable, front page with maybe our face on it, the idea that we want people to actually interact with our app requires the adding of a database. So when you guys uploaded your pictures into the app, if it was just a front-end page, I would not have been able to do that. So we had to add a database that actually takes the information. In the case of my app, I said, hey, I want to accept pictures and I want to accept text. Let's keep each of those things inside of a database. So inside of Replit, we actually built that database. And let me see if I can show. All right, there we go. If I pop out of here. All right, so the database in here. There it is. If we go to Tools, and we go to Database here, you can see that we've got a development database for when we're testing, pre-publish, and then after we press publish on our application, we've got what's called a development or a production database as well. So all of the pictures that you guys put into our wall are put into this database, and all the comments that were associated with that are also put into this database. If I go over to all databases and go into the development database, you see that I've got a different number of rows. I've got 22 rows as opposed to the 32 or 33. So the difference between doing something locally before you publish and then publishing it, it's live to the world, development versus production. So after the database publish, adding APIs. So if we wanted to use one of those third-party services, typically you can do stuff like weather, you can do stuff like time series, stock information, you can do stuff like, you can literally pull Shopify information or pull information from any of your favorite services into your Replit app, such that every time it loads up, it's pulling the information that you want presented into the actual interface. We've got plenty of APIs that you can connect with. The shortest line in this whole presentation that will allow you to do something cool is add Replit auth to my app. If you do that, you're going to add a portal basically for folks to log into that'll look a little bit like this. You know, you can have Google, you can have Apple, you can have any of the typical ways that people log into applications. It takes like 5 or 6 words to add authentication so that users can kind of log their session information, log their pictures, log their text, and very easy to do and implement. And a couple of words on user testing and research are in here. When we get past the technical hurdle, there are students that are going to be marching towards actually experimenting in markets and seeing if app A is better than app B and actually capturing that market. So I'm excited I'll tell you this last story as we wrap. There's this student from Penn State. He had 3 colleagues, so the 4 of them visited the Replit offices. They said, hey, we graduated recently and we're kind of building the business, continuing to build the businesses that we started in college. I said, oh, that's cool. Like, so each of you like did businesses in college and like attended classes. And the guy said, oh, kind of. So he said one of us out of the group for every class was like the leader. So one of us would go to that class, learn all the things, and then come back and teach the rest of the group. They would take 4 classes per semester, and each of them would be the leader. I said, what do you do with all of the extra time that you like weren't in the other 3 classes? They're like, oh, we built businesses. So they built 4 different businesses in the span of 4 years. I said, oh, like you make any money? He's like, yeah. I said, like, what, 5 figures, like a couple grand? He's like, no, each of us made like $1 million each over 4 years in ARR for the businesses that we started. So I started to think about, oh, maybe like instead of GPA, transcript, resume, the idea that you could learn information and monetize and like participate in the economy with that information across 4 years, such that you walk across the stage with 0 debt at the end of your college experience. Maybe that should be like a goal that I have for like the education team and like part of the message that we talk to teachers and faculty and other students about. Thumbs up if you think that that's a reasonable idea. That sounds. I think I would hire those people to join my team. Entrepreneurial, bootstrapping, scrappy about these things. So anyway, the idea of multiple people using one workspace to accelerate the build-out time. I'll send you all these slides as well as we're coming. I only got 3 minutes left, but I'll end with some limitations of vibe coding. The idea that you do need to know a little bit about how product building works in order to figure this stuff out. A lot of the times you'll get errors that are unfamiliar to you. So the idea that you can screenshot that in Replit and drag it into the interface and say, hey, I don't know what this actually is and how to fix it. The same tool that you're using to build out your application is the same Replit agent that you can ask questions to in order to get unblocked and unlocked so that you don't have to wait until a human being can help you. You can literally use a Replit agent to get unstuck and build at the same time. In terms of complexity and technical debt, I think debugging is probably the most useful skill on this list, and learning how to do that if you're not technical is a lot of trial and error and is a lot of time you'll spend with agent learning the things that traditional engineers and traditional folks in computer science learn in class. All right. vibe coding when it needs guardrails. We typically talk to technical people about some of these things, but what I'll say is like security, there's security scans before you publish, and then there's validations and things that you should know from a user interface perspective, like what's appropriate and what's not. We, on a platform side, do as much as we can from a Replit perspective to protect the users and to protect the builders, but there's some common sense and some things that you also have a little bit of responsibility for as well. With that, I'll just say thank you for your time and attention. I appreciate all of your ears and are excited to communicate and collaborate with some of you if any of these ideas resonate. Thank you guys so much.
Brandon. So we're going to start back up our talks, and our first one we have is Peter Rathie with Neo4j. You want to come up front, Peter? Yeah. What's that? Philip, sorry. Did I say Peter? Philip Rathie.
I'm going to try this mic out. Okay, that's pretty good. Cool, great to be here. You've probably heard a lot about things like knowledge, context, semantics, memory, ontology in AI these days. They're all separate topics in a way, but I'm going to bring them all together, actually, with this topic around the knowledge layer. And this comes out of working with thousands of customers over the last few years and seeing that there are a number of different patterns in which they take all of those things and use them in one common way. And that pattern is the enterprise knowledge layer. So here you can see a simple picture of apps, agents, tools accessing a knowledge layer that gives agents what they need from a data and knowledge perspective. And it brings together data from across the enterprise, you can see on the bottom right, all the different operational data sources, and on the bottom left, from the different analytic data sources. And now this isn't a lift and shift. The knowledge distinct from data doesn't mean everything about everything. It means let's pull up the signal from the noise and let's connect it up. Those connections are essential here. And then likewise, you can start small and then build up. So it's also very incremental. And if I look at the function, what's it doing? It's storing structure, context, and meaning. It's providing a uniform memory and retrieval layer for agents. It also bridges human and machine understanding. And this comes back to this idea of neurosymbolic AI, which is not new. It's a few decades old. But it's coming back with graphs in this different way of, you try to introspect a model or introspect a vector database, and those are unintelligible to a human being. Whereas with a graph, you can really understand as a human what's going on, and then you can execute it as a machine. And then it links and unifies your data sources and objects and stores data as a graph. Here are a few examples of this in action. So one is Walmart's People AI Knowledge Graph and Graph application. This is an agentic application usable by Walmart's 1.6 million or so employees that helps them navigate their career journey. So what does the graph look like? It's all the people, the reporting structure, the history of the reporting structure, their skills, how those have accumulated over time, what projects they've been on, what all the different open jobs are, and what their job requirements are. And it turns out that if you put those all into one graph, you can recommend someone's career journey simply by connecting the dots. It's almost like solving for HR by degrees of Kevin Bacon. And importantly, this then feeds a model, so there's a model in between the human and the graph. But the questions actually can be answered either by the model, by feeding it more context, or you can actually get an answer from the graph and run it deterministically. So you have this powerful optionality of running deterministically or non-deterministically. Here's another example at Uber, who has a different kind of graph. It's the rules graph. So Uber operates in 15,000 cities. They have different offerings in those cities. Those are called different things. There are different laws, regulations, as well as Uber's own reasons for varying the offerings. And those rules are stored and executed in the graph. And I brought one more example from a major gaming company. This is one of the largest gaming companies in the world, where you can see an API, a conversational AI accessing an API layer, accessing a multi-agent system, and then using the graph as a semantic layer. And semantic layer here means taking business terms and concepts, the relationships between those, and then mapping those to physical infrastructure and down to data infrastructure and where you can find the data. So agents use the graph to get a map of where to go in the enterprise to find data. So these are three different kinds of graphs, and you could say this is semantics and ontology. Earlier was the domain graph. You have a rules graph, which is a form of memory, procedural memory. And what they have in common, and the key core insight behind why these people chose to build the systems in this particular way, is that they saw that their data either showed up as a network, so in the real and digital world that AI needs to engage with, it tends to show up in a few ways. It can show up as a network. Computers are networked, social networks, communications, biology, ecology, transportation, and so on. Or as a hierarchy, like the Walmart HR example, which is actually multiple hierarchies and journeys, and then likewise with customer journey, patient journey, and the like. And so if you can choose to represent those in tables, and in fact that's been the dominant way over the last few decades, but there's a newer way to look at data, which in fact, as of 2 years ago, is an ISO standard. So for those of you who might not be familiar with this, for the first time in nearly 40 years, the International Standards Organization blessed a new data model in the database space, the property graph data model that represents data like this, the way we're talking about, for dealing with data that shows up in the real and digital worlds as networks, hierarchies, and paths. Now, why do you need a new model? Why isn't it enough to deal with what you've got? Well, let's look at what you've got. You can use a foundation model, but they've been trained on the world's data, not on yours. Okay, well, then I can train my own small model, but that's expensive. And then let's say I get over that. The minute I train the model, it's already out of date. And then everything I've trained my model on becomes fair game for answering any decision by any agent for any purpose. And we know that you have all kinds of rules around access controls inside of an enterprise. It can also still hallucinate and lack discernment. And it's a black box. Data structured as static rows and columns is great. That's where most data is. And that's good for answering fixed and simple questions. But if my questions get super intricate and complex, and I don't know what in advance what the next question is going to be, then actually this is where graphs have always shined. I've been doing this for more than a decade, and this has been the main reason for using graph technology. Now, I can look at other unstructured forms of data, but that tends to be difficult to mine and make sense of. And as I pointed out earlier, vectors are completely opaque, and it's arguably like a one or two trick pony. And then organizational data is spread across silos. So how do I bring the knowledge from across the silos so that my agents can share the intelligence of the entire company, not just what's in one system? Now, many companies have been doing this to the point where Gartner's gone out and said, look, this is a clear trend. And their recommendation to data and analytics leaders is they must redesign the data and analytics architecture to make the context layer the central brain for AI agents to deliver trusted intelligence. That's exactly what we're talking about here. Now, let's look at the requirement agents have of knowledge. Now, agents are highly interactive, so they can't just interact with like a data lake or a lake house. They need a real-time system where they can have low latency retrievals, as well as update the system so that you can have a virtuous cycle of self-improvement. You also need to be able to store structured, unstructured, and semi-structured data, number 2. Number 3, you need to bring together data from across the silos. Now, your data lakes and lake houses bring data together from across the silos, but at the expense of losing the connections between them. You're centralizing everything, but you're not connecting it. You need to be able to have a RAG corpus and I would add a graph RAG corpus. And then you also need data access controls for exactly the reasons we were talking about earlier: corporate firewalls, security, privacy. So this is what agents need. Now, if I bring all that together, this actually answers all of that. This is really a zoom in of what we went into earlier. And at the highest level, you've got your data that's connected as a graph, your domain data, and that can be your own domain, that can be reference data that you get in from third parties. And then you also have the option these days of running graph queries against data lakes through technologies like Neo4j virtually, so virtual graph is on there. In the ontology bucket, I include the semantic layer. So this is everything around meaning, your business meaning, and then how it maps to where your data is located. This is like a business and a technology map. And then last but not least is memory. So conversational memory is just all the different texts and prompts. But then, much like the human brain, as part of the process of sleeping and memory consolidation, gives you long-term memory, which is what are the things that matter and how do they connect. Long-term memory tends to be best stored as a graph. Procedural memory tends to be best stored as a graph. Context and decision traces, which is another form of memory, likewise. So what's the role of a knowledge layer? This is a whole presentation that I've rolled up into one slide because we've just got a short amount of time. I've got some learning resources at the end. But number one, it's providing context for agents for better answers. I'll show you a link to a paper that just came out by the UK's Center for Data and AI Innovation that complex, let's say a rich academic piece of research that shows that you get substantially better, I think it's more than twice as many questions are answered versus not, with 80% better fidelity, lower hallucinations, and fewer tokens. So very, very powerful. It can connect the silos. It can give you knowledge transparency and an option for deterministic processing. It can respect data access controls. And then, surprisingly to me, it can handle complex questions much better. I've had customer after customer come back and tell me that AI models do a much better job of answering a complex question expressed as human language using graph queries than using a relational query. And that's because the graph query language, GQL or Cypher, you might express a complex question as in 5 lines that's 200 lines in SQL. It's a much more terse representation that's nearer to human language. Now, what are the kinds of data concretely in the enterprise? There are 2 ways you could look at this. One is, let's say, a breadth-first or top-down view is the enterprise itself is a connected organism. So you can build a map connecting up the silos. The other one is bottoms-up. Here you can see you have the product graph, which is a product hierarchy. And out of that, you have all these different use cases underneath that are supported, recommendations, product pricing, inventory. But then that connects, if you connect that into the supplier data, you can do supply chain optimization, and so on and so forth. We saw the employee graph, career journey, et cetera, et cetera. And you can build these out incrementally. I don't have a lot of time to go through this, but I'll just flash it. This looks at the top AI use cases, just looking at data coming out of the top systems integrators and some of the top AI labs, mapped to the kinds of graphs that show up, mapped to the kinds of AI motions and processes that are enabled. And you'll see things like multi-hop reasoning and agentic workflows in there. So drilling into reasoning, one takeaway I'd like to leave you with for today is that the knowledge layer isn't just a passive place where you store information. It can actually do various forms of computation. So I'm running short on time, and I'm going to zoom through these, but graph querying, which is different forms of pattern matching and filtering, graph algorithms, clustering, link prediction, and so on, similarity in search, GNNs, which is a topological vector, another kind of vector, and then graph visualization. And then The key advantages here are GraphRag, which gives you improvements in accuracy, multi-hop reasoning, which helps agents perform more complex tasks, semantic maps, map of the enterprise, decision traces, which is a whole talk in itself. I'll give you some breadcrumbs, and then memory. So I'll just leave you with a few resources, and then we'll drop. One is, I wrote this piece 2 years ago. It still holds up, introducing GraphRag. Next one just was published 2 weeks ago, describing the enterprise knowledge layer. So it's a kind of a prose description of this talk. Number 3 is this paper that I just mentioned, showing that agents using GraphRag versus vector only are 80% more truthful, answer twice as many questions, hallucinate less, and then it's less expensive. You use far fewer tokens. And then last but not least, if you grab this QR code, we've prepared a special landing page for all of you with some further learning resources. One of them is Andrew Ng was here today. There are some deeplearning.ai courses, and then Neo4j has our own Graph Academy with lots of learning there. So I'll leave you with that. Thank you. Looks like I'm just on time. And thanks, and I'll encourage you to go and find your own graph.
All right, thank you, Philip. Next up, we have Josh Albrecht. You can come up with Imbue. Welcome.
Okay. Today, we're going to talk about the importance of building open software and building punk software. A lot of the talks that we've seen have been about all these really cool platforms and everything. That's great, but it turns out you can build pretty much whatever you want yourself. So that's what we're going to be talking about today. I really like this quote as a place to start. So it's, "This present moment used to be the unimaginable future." And this is by Stuart Brand from the Long Now Foundation. I think if you went back 5 years and you asked people, or you told people what we could do today with coding agents, they'd be like, what are you talking about? There's no way that's going to happen. So things have come super far. And we have AI agents that let us think and dream and create, the unimaginable future that will come in 5 years from today. But today, frontier AI is fully controlled by a few corporations. And there are plenty of hypothetical dangers. For example, what if an AI company released a model like Fable and then unreleased that model? Or what if they increase the price dramatically? Or what if they ban your account? Or what if they change the terms of service so you can't do the same thing you were doing, like, say, AI research? Like, can your business survive those events? Can the thing you're working on, the thing you care about, survive them just disappearing on you? But these dangers are not actually hypothetical anymore. Like, the largest AI labs today are now routinely hiding the thoughts of their AI agents, hiding the logits, making it harder to do third-party audits, hacking into your website, as we saw a week or two ago, refusing to help you fix vulnerabilities by refusing to work on cybersecurity defense, silently degrading performance, as we saw from Anthropic a few weeks ago, competing with your business, as we see from Anthropic making their own drugs after partnering with people, or making their own Claude Code design after partnering with Figma, or banning your account with no recourse. So there is an existential risk from AI to you. Not to the human race. We're not about to go extinct. But your business and livelihood, that could. So I think that if we want a good future, our thoughts and our agents' thoughts need to be fully under our control. This can't be something that we rely on a third-party remote computer to provide and that can be turned off at any time if this is how we're thinking. If we're using this stuff for education, for building our own tools that we run our lives and our businesses on, we can't have something where it's not actually part of us. So how do we do that? I think we need to do that by making the whole stack open. So it's time for a free software revolution, to take back control, and that's what punk software is about. It's a software uprising. So what is punk software? Well, it's a term that we randomly made up when some people DM'd us on Twitter and was like, oh, I love your punk software stuff. It's like, okay, cool, that's great, like, let's take that, let's run with it. By punk, we mean decentralized, minimal, DIY. It's more of an ethos or a vibe. It's a way of thinking about software. The original punk, music movement was very much about doing things yourself, right? Being bad at playing musical instruments, being bad at writing code, that's fine. We want to take that ethos and apply that to software. By punk software, we mean software you build yourself. You can share it. You can help other people build it. It's meant to be something that you understand, you can explore, you can create, and it's yours. So what makes good punk software? Well, I think there's 5 things. 1, it's individual. So by this, I mean it's something that is both controlled by you, fully a part of you, but also something that you can customize and make more yours. Can you control everything about it? Today, there's so much open source software that this is possible. We also want it to be decentralized. So it's not just something that can easily be turned off. It's not something that runs on someone else's server. It's something that is everywhere. It's diffuse. That's really what we mean by democratization and by empowering people, is literally you having tools that are yours to allow you to do what you want to do. 3, we want this stuff to be open. So we want software to be something not just that's open source where you can read the code, or not just open weights, but open in the sense of you can actually look at what is happening inside of the model, inside of your system, inside of your operating system, and understand what's going on. You can learn, you can educate yourself, and you can build larger systems outside of that. Now, another side benefit of it being open is that the agent can look at it too, and this turns out to be extremely useful for making much more useful systems. We also want this to be anti-monopolistic. And by this I mean making tools that fight against centralized power and try and make individual people in control of their technology and their lives. We don't want a place where all of our data is locked in some silo that we don't have access to. We don't want a place where suddenly the prices can go up and we can't do anything about it. And finally, we want to make moral software. So I think people have forgotten a little bit that the point of software is to do things in the real world. Recursive self-improvement is all fine and good, but at the end of the day, what are we improving at? We want to make things that are good for us, are good for the world, and so there's a moral component to punk software as well. So what does this look like in practice? Well, in practice, there's a lot of stuff that goes into making these like agentic AI applications and systems. So there's a whole set of stacks, and we want open everything. So starting at the very bottom, we want open infrastructure, things like Linux, things like Docker, things like SSH. We have a huge, rich ecosystem of open source software to pull from. We want open source inference. We also want open source models, things like GLM or DeepSeek, or things like Nemotron or Inkling. We also want open source harnesses, things like Codex, OpenCode, Klein, Goose. We want, as well, the next layers that go above these. So how do we coordinate those harnesses? How do we coordinate agents? Things like TMUX and Herder and CMUX are ways of playing with multiple agents and getting them to communicate and coordinate and building larger systems out of these smaller components. And finally, we want top-level things that use these agents to do something useful at the end of the day. So today we're going to look at 3 that we are currently working on at Imbue. So the bottom 2 are called Manager, and then a specific plugin for Manager called Manager Donate, and the third one is an application that we're building called Minds. Manager is an open source tool that you can use to coordinate agents that's available free today. It's online, it's on GitHub. Manager Donate and Minds are 2 things that are still in beta, so if you want access, just email us. We'll happily send it over. In fact, they're technically open. You can go find them, but it'll make more sense if you email us. Okay, so the first one, Manager. So the point of Manager is to commoditize the AI models and compute providers. So by this I mean, make it so that you can use any AI model you want and any compute provider you want. The core idea is to make AI agents into a building block for larger systems. If you can get them to do whole tasks for you, then you can build up a larger system that doesn't tie you to just Codex or just Claude Code. So the idea with Manager is to stop requiring AI agents to be interactive. We don't want you sitting there hitting, yes, it looks fine to run this gigantic bash command, I guess. Like, that's kind of a waste of your time. You want to be thinking about how to run these things in ways that compose and build up larger systems. So here's a kind of overview of what Manager is and how it works. So it's a thin layer that sits in between your application and any harness and any compute provider. So you can use Codex, Claude Code, whatever. You can use AWS or GCP, whatever. But the point is you don't have to think about that. Instead, you just have a very simple command line tool where you can say Manager create and launch an agent. Or you can tell it exactly where to launch it. Or you can tell it, you can give it a name. Or you can tell it what harness to use. You can still pass in extra arguments, you know, but the second to last one there, model create, tell it exactly to use Opus. Or you can send it a message. So the point of Manager really is that you have these other primitives as well. So you can use something like Manager message to send a message to the agent. Or you can use Manager transcript to see the messages that have already been sent both from you and from the agent. And this is unified access across the different coding agents. So instead of you having to worry about the format for Codex and the format for Claude Code are different, you don't have to worry about that. Manager takes care of this sort of layer of interoperability. The same thing for compute. You also have things like Manager List to see your agents, Manager Connect to connect directly to one. When you call that, you just end up right in the terminal running as if you were running Claude Code natively, but that Claude Code might be running on AWS or on Modal or locally. It doesn't matter. You get to interact with it, send it on its way, disconnect, and you're all set. You have things like Manager Wait to compose other larger things, Manager Snapshot. It just is a big toolkit that allows you to make these higher level systems. There are many more commands. You can go online and see the rest yourself. So if we score this in terms of punk software, is this good punk software? I think so. I mean, that's why I made it this way. So is it individual? Yes. One of the things that's different about Manager is there's no service. We're not trying to sell you a SaaS thing. There's no remote database. Everything is local. It simply asks every time you run it, are there any things in AWS? Is there anything local? Okay, great. So you can control everything about this. It's easy to make plugins, change the settings. It's all just directly controlled by you. So it's fully decentralized, completely yours. It's MIT licensed. The point, I think, is relatively anti-monopolistic in that it's trying to commoditize AI models and compute providers. It's trying to make it so you're not locked into their sort of vertical ecosystems. And it has at least a little bit of a moral character in that it's trying to directly empower you as an individual. Okay, second thing that we'll look at today is a plugin for Manager. This is called Manager Donate. It's very easy to make new plugins. This particular plugin we're making to make it easy to donate your extra tokens to science. So the problem that we're solving here is that you don't fully utilize your subscription. In theory, your subscription gives you I think it's about a $100 subscription per month for Claude Code. If you max it out, it gives you about $4,000 on the API. But you don't always max it out. But if you come to the end of the week and you haven't maxed it out, why not give those tokens to a scientist who would happily do some useful work? So that's what this allows us to do. And it's built on top of Manager, which makes it easy for the actual implementation. So Manager can run the tasks from the scientist in a sandbox for you, or in the local Docker container, so you don't need to worry about them running untrusted code. It also can understand the usage from your subscription, so you can make sure that it doesn't use tokens that you were actually going to use yourself. So scoring this on punk software, how punk is this? I mean, it's fully individual. You can control exactly how much you want to donate, how much you don't want to donate, which causes you want to donate to, et cetera. It's fully decentralized. The idea is that scientists will be able to just post whatever research they want done. Your system will go off and pull that, compute it, send it back. It's completely open source, anti-monopolistic a little bit, I guess. I don't know how many monopolies there are that are doing open source distributed AI science. And moral, yeah, I mean, contributing to science, I think most of us probably feel is a good thing. So the third thing we're going to look at is the application that we're building on top of Manager that's more for regular people than for software engineers. So Minds is an application that's meant to be personal intelligence, sort of like a personal computer. The core idea is that you run the language model alongside the software that it creates. So instead of creating an application like in Replit and then deploying it, and you have a database, and you have production, and you have migrations, that's just a bunch of noise. That's a bunch of extra complexity that you don't need when you're trying to make a personal dashboard or a little script that runs every day. So the idea is to build on top of Manager, make it easy for people to run these things in a fully open source way that's completely under their control. So at its core, it's about running a little virtual machine, either on your computer or remotely. Inside of this machine, Manager coordinates the coding agents and uses them to make the different applications. These applications are whatever you want. You can have it go do one-off tasks. You can have it triage your inbox. You can have it rank science fiction short stories that it thinks you would like, whatever you want. But the point of Manager is to abstract across, where is this running? What compute provider, what AI provider is doing this thing, so that the thing is fully under your control. If you want to tell it to ask questions about Tiananmen Square, or you want to ask questions about cybersecurity, it'll flip between the models to make sure that both of those get answered. So if we think, okay, how punk is this? The reason that we made this is to make a sort of individualized way of making coding agents. So it's completely under your control, it's completely decentralized, it's completely open source, and it's meant to not lock you into a vertical system like Claude Code, Cowork, et cetera. So I think it'd be great to have you join the revolution, help us make punk software, make the whole stack open. We saw some examples. And if you want, feel free to get involved by looking at this QR code. If you want to donate your tokens to science, if you want people to give you tokens for doing your own science, if you want us to highlight the punk software that you've made, if you want to join our punk software hack nights, or join our Slack, or try out Minds or any of our products, please just email me. We'll happily connect and would love to build this stuff together.
Next up, we have Woosak Kwan with Infract.
Thanks for joining today. I'm Woosak. I'm a co-creator of VLM and also co-founder of Infract, a startup built around VLM. Today, I wanted to talk about what agents demand for the inference stack and how we are evolving VLM, open source inference stack, to meet these demands. Let's get started. So, key intro for everyone new. VLM is an open source LLM inference engine to make LLM inference efficient and effortless. It started about 3 years ago here at UC Berkeley during my PhD, and has been growing rapidly ever since, even now. And we hit it 88K GitHub stars, I think, pretty recently. Importantly, this is a very highly collaborative project across academia and industry, with major contributors including Red Hat, NVIDIA, AMD, Google, Moonshot, and us at Infract. And it's also being widely deployed in industry for production inference. There are two main ways to use VLM. I'll go them very quickly. The first is the LLM class, which is a Python interface for offline batch inference. You give it a Hugging Face model name, and you call the generate, and that's it. So VLM automatically handles model loading, optimization, scheduling, and memory management under the hood, so that you don't need to care about it in utilizing GPUs. And it generates the text completion of the prompts and returns to you. The second is online serving, VLM serve. This is a single command that you can get a OpenAI compatible endpoint from. And obviously, we also support Anthropic APIs too. Any agent framework that speaks the OpenAI or Anthropic API can also work out of the box, since the API layer is pretty standard. So that's how you use VLM in the first place. But as you can see, the API itself is pretty much similar to the few years ago, right? So it actually didn't really change that much for agents. What has changed a lot for agent is everything underneath it. So yeah, specifically, at a high level, agents change the inference problem along 3 axes. First is large models, right? The frontier agent models like Kimi K3, DeepSeek V4, are trillion parameters MOE. And that forces us to get serious about model parallelisms. Basically, it gives us a lot of opportunities for us to parallelize the model in many creative ways with different trade-offs. I'll talk about it in more detail later. Second is long context, right? Agent sessions run for hundreds of turns, up to 1 million tokens. And the context only grows over a session. So managing KV cache of these the previous turns is very important for inference performance. And we definitely need to ensure that the inference framework is not recomputing any of the tokens in the previous turn, because otherwise it will be a lot of recomputation and a lot of waste of compute. A third is enormous token demand. Now that agents are getting really, really smart and so capable, so that there are actually now near infinite demand, now near infinite places to deploy it. So the demand is effectively unbounded. It's growing faster than the GPU supply. So the inference engine and inference serving has to adapt to it. And our solution to this is to basically enable this efficient inference for more diverse hardware backends, so that we can utilize all available compute to generate tokens. Okay, let's get into more details. Yeah, let's start with parallelism. So to efficiently serve such large models, like VLM today supports mainly seven different types of parallelism, like including tensor, pipeline, data, experts, like sequence parallelism, and like 2 different kinds of context parallelism. You may recognize some of those in from the training world. Like VLM supports them all, and plus the ones that don't exist in the training, like decode context parallelism, which is parallelism around the KV cache. As a general purpose engine, like VLM efficiently implements all of these parallelism and also like mixture of them, right? However, like we found that that's not enough. The important thing is that like these parallelism need to be properly selected and tuned, like for the target model architecture, the target cluster setup, and also the target workload shape. There's no universal winner, or there's a universal solution. Let me show you what this tuning looks like for a real model. So this is like DeepSeek V4 Pro, like running prefill of it like on B200 GPUs in the desegregated serving setup. Like so, these setup GPUs only perform prefill. Basically, the most straightforward way to deploy the model, like DeepSeek model for like prefill on this GPU cluster, is just using like 8-way tensor parallelism. That's the most standard and like simplest way to do it. However, the winning configuration is pretty much different. Like it's like in this like particular workload setup, like it was like 2-way tensor parallel times like 8-way 2-way pipeline parallel times 8-way like tensor parallel plus sequence parallelism and expert parallelism, like deployed across 16 GPUs for each model replica. So we found that this gets like much lower TTFT, basically like the latency on the first token, and also much higher like throughput per GPU compared to the straightforward like single host 8-way TP baseline. The reason being is, yeah, like it's actually pretty much complicated, so I'm not going to much details. But the reason being is like pipeline parallelism is like enabling the parallelism between different chunks in the long prefill. Sequence parallelism enables more communication and computation overlap, and expert parallelism gives a better gem shapes, better like matrix multiplication shapes compared to the like 8-way tensor parallelism. Yeah. The takeaway is that basically there's no winner, and also like this like we need to basically this large models makes this kind of like model parallelism and sharding a necessity, and there are many different ways to do it. And like depending on how you choose and like tune these like parallelism degree, like the performance like varies a lot. And basically in this agentic era, you need to have the right like insight and performance model to set the to configure this in the correct way. And VLM basically provides the common substrate that you can basically play with all these different parallelism. So the second is like KV cache. So speaking of it, so like the one very critical characteristic of the modern LLMs are that they are basically hybrid models. Like they are like basically hybrid in the sense that they're interleaving the regular full attention with some other more efficient attention mechanisms like sliding window or like linear attention such as Kimi delta attention. And this is basically the thing that makes the 1 million context lengths feasible, because global attention itself is like takes too much memory, like if you want to really go to 1 million contexts. However, in theory, this is very efficient, but like this in practice, this creates a lot of like a real systems challenge. Like basically these layers, like with different attention types, have completely different memory behavior. Like full attention, like the KV cache of full attention grows linearly with the context, while like linear attention, like KDA, like keeps a fixed size state per sequence. We're still going, I mean, like regardless of the actual context lengths. So like, how should we curve up the GPU memory between them? Is a real one of the like important systems question. The straightforward solution or answer to this question is static partitioning, like reserve X percentage for full attention, Y percentage for the rest, things like that. This works, but the problem is that the optimal split between the two depends on the batch size and context length, which is pretty dynamic over time during inference. So the solution in VLM is dynamic partitioning, so which is basically using one shared memory pool for GPU memory, and each attention type with different memory behavior gets its own allocator drawing from this shared memory pool. So yeah, in a sense, the full attention allocator, recast to this shared memory pool of the specific number of tokens, while in the KDA allocator, because it's a linear attention, allocates one giant block for the entire sequence. And we have a logic to dynamically share the same memory space between the two. Yeah, this is also pretty much detail, so I'm not going to too deep. But basically, this is one critical feature in VLM that allows you to not worry about how to handle these different types of attention and the memory split between and VLM basically automatically rebalances the memory space between the two so that no GPU memory is wasted. Okay, yeah, regarding KV cache, so also another thing is that important thing is managing this KV cache within the GPU memory space isn't enough, right? Especially the agent sessions are pretty long-lived and also very intermittent, which means basically the model generates and then generates some output tokens and then waits, right? For tool calls or sometimes for human response, and then it basically continues. And during those waits, the KB cache is somehow stored in some area, right? It could be stored in GPU memory, it could be stored in some other memory, right? To store this KB cache unused at the moment, we basically use this concept of KV connector. This is basically allows to leave this idle KV cache, store this idle KV cache to external memory like CPU memory or disk, and bring it back when it's needed. And yeah, here basically we shortly speaking, basically we did a lot of efforts to design this abstraction and make sure it is well working with third-party libraries like Mooncake, and also it is well working with other KV transfer mechanism like prefill desegregation. In the prefill desegregation case, the KV the movement of KV cache is pretty dynamic and complex because it needs to move between prefill instance to decode instance, prefill instance to the distributed KV storage pool like Mooncake and things like that, and we basically set up the infra to efficiently handle this, so that again in the many turn agent sessions we never recompute as long as the storage allows we never recompute the tokens in the previous case in the previous turns. Okay, the last part is hardware. So basically we believe the economics of tokens have is flipping. So as models get smarter and more intelligent, the value of a token far exceeds the cost of generating it. So therefore, naturally the demand is exploding. We're witnessing that. And honestly, there are not enough GPUs in the world to serve it. So the question becomes, can we use all the available compute on Earth to generate tokens efficiently? Yeah, and VLM basically aims to answer that question. To achieve the goal, we support more than 10 hardware backends today. Obviously, NVIDIA GPU is our major focus, but we also work on Google TPU, AMD GPU, and many other hardware chips from the industry. And they basically have the plugin structure to VLM to share the core part of VLM while they're customizing some specific parts for their hardware backends. And yeah, obviously this makes more sense because yeah, the API in the inference space is pretty much standardized, right? You can still use the same like OpenAI or Anthropic API, and just that with different hardware under the hood generating the tokens. Yeah, like for the sake of time, I'll probably need to skip the slides. But basically, yeah, we got a lot of lessons from like supporting this hardware, and we're actively working on it. But like the TLDR is that like bringing up this new hardware and making it efficiently supporting the new models is I think getting better because of coding agents. But on the other side, it also still requires a pretty like rethinking the entire inference stack from ground up. So yeah, like we're actively working on it. Yeah, and for a summary, yeah, like in the agentic era, basically stresses the inference on 3 axes, and VLM answers each of the one, like here. Large models with workload-aware model parallelism, long context with a dynamic and hierarchical KB cache, and like exploding token demand with diverse hardware backends. And everything I showed you today was open source, so please come join us with different places. Thank you.
So next up, we have Benghua Zhu with Radix Arc. Welcome.
Today I'm going to introduce Ashland Mouse, where we build the frontier AI infrastructure within Radix Arc. So the mission of Radix Arc is to make frontier-level AI infrastructure open and accessible to everyone. And to achieve that, we're building in open source right now, where our inference engine, Ashland, is adopted as a production inference engine all over the places. And then our recent R framework Mouse are also gradually picking up as a production like frontier level infra for post-training. A quick intro of Ashland. So we view that as a production-grade open source inference engine, where Ashland itself is supporting language model and vision language model inference. And we also have Ashland Diffusion, a relatively newer project on image and video generation, and then including also like VLA and word model inference as well. And third, more recently, we have Ashland Omni, which is more targeted around ASR and TTS model, more around the audio side. So altogether, like the entire Ashland ecosystem is more optimized for agentic workloads, and we provide really performant day zero model support, and also very broad hardware support, including NVIDIA, AMD, TPU, Trainium, Intel, and so on and so forth. We also have Miles, which is our enterprise-grade reinforcement learning framework. So it's forked and co-evolved with Slime, with more features on NVIDIA and AMD latest hardwares. Slime is a project that like Zhipu AI built together with Ashland community for their GLM model series training. So it has been battle tested on production training at very, very large scale. And for Miles, we also provide day zero support for all the open models, including Kimi, GLM, like Inkling from Thinking Machine, like Nemotron from NVIDIA, etc. So at day zero, when the model are released, you can just directly use Miles for training and customization and use Ashland for inference. So Miles natively use Ashland as a rollout stage, and then use NVIDIA's Megatron as a training stage for the best performance here. So today, Ashland Miles are already adopted widely by different enterprises and rising star companies, like all the hardware companies, all the hyperscalers, enterprises, AI labs, especially new labs, and also developer tools and new clouds are mostly like widely adopting Ashland Miles in their part of their infrastructure for inference and training. There are also different ecosystem collaboration where we work with Google Cloud very closely for improving their throughput for their internal inference stack. And also Cloudflare, IBM, like XAI, Meta, they all use Ashland as a backend for their inference engine. So to us, 2026 is actually the year of agentic infrastructure. So for inference side, the demand is exploding, and actually the challenges are very unique. And for training side, actually every detail matters. And it's still early, but everything needs to be done right so that you can train the model without hurting its generalization capability. So I'll briefly go over the challenges in both inference side and training side with the introduction of agentic use cases. So for agentic inference, the first thing people care about is high cache reuse. People see DeepSeek V4 has a really low cache hit rate price, And such high cache reuse is actually very important to ensure that, and also make sure you have really high cache hit rate and to reduce your entire cost of serving. And second thing is that people are now all moving towards trillion number of parameters of models. So how do you handle those large models? It's also bringing more and more challenges to open source stack. And of course, like for context window, right now 1 million contexts is already the norm. So there will need to be more optimization around super long contexts. So how does SGLang address those challenges? So first, for high cache reuse, we're bringing like 2 unique technology introduced by SGLang. One is unified hybrid Redis cache, which is designed for all the recent hybrid models, where you can make sure the previous cache will run smoothly with all the hybrid models and new architectures introduced recently. And second is our high cache design and system, which basically enable people to move the KV cache down from HBM to DRAM and even to your external storage, so that there will be most efficient way of handling KV cache in between different memory layers. So as a result, as a concrete example on Qwen 3 coder, we get to greatly improve like cache hit rate and also TTFT and throughput as well. The second challenge is large model scaling when it comes to 1 trillion, 3 trillion, and even larger models. So the standard technique definitely include all the 5D like standard parallelism, like data parallelism, tensor, context, pipeline, expert parallelism, etc. There are also like newer parallelism strategy, like DP attention, like DCP, and PCP as well. And beyond that, there are also new combinations of deployment strategy. Like people start from collocate, but then gradually move towards like prefill decode mode, prefill decode disaggregation mode for a larger scale and more imbalanced prefill decode deployment. And now for vision language model, there are also like EPD, where you also disaggregate encoder in this case. And there are also different runtime optimizations around SGLang, where there are different ways of supporting spec decoding from Eagle to MTP to DFlash and recent DSpark from introduced by DeepSeek. There are also like scheduling designs, including the overlap scheduler, and then our most recent spec v2 for better support the native spec decoding speed up in inference stage. And third, and also like perhaps very important context, is also related to how people handle long context, especially when it comes to scaling to up to 1 million parameter, 1 million context window. So the first one is chunk pipeline parallelism, where we get to essentially, instead of sending the whole prefill sequence at once, we get to chunk them and chunk the entire long prompts into different smaller chunks, and then process them like in parallel. And the second thing is a different dimension of chunking, or parallelism, where we split sentences or sequences into across GPUs for long context handling. There are also specifically sparse attention related optimization we did with high sparse, where we get to process the full KV with a hot buffer here, and then to ensure those sparse attention get more, basically occupy less memory and result in much higher throughput in this case. So by combination of all the techniques and also all the like fine-tuning we did, this is a very concrete example where at day 0, our GRM 5.2 performance is already the best. And then over the time, we already are able to achieve like over 2.2x improvement and achieving like up to 500 tokens per second per user in this stage. So in summary, SGLang has been keeping shaping the frontier capabilities and in a fast, verified, and optimized fashion. We're the first to introduce a lot of new techniques in large production, including radius attention, like spec decoding, PD disaggregation, like sparse attention, and also native RL support with Miles, and later recently, like DFlash, DSpark, and high sparse as well. So the next, I'll briefly mention about agentic training part. There are also a lot more challenges introduced by long context agentic training. So one is that people now are looking at much more diverse environments. So it's not only about more tool calls and longer context, but also about some environments might be very hard to execute, and it might be even requiring like lab experiments to get the reward signal. And the second is also about train-inference mismatch, which is a very popular topic in frontier labs these days, where if you have very large train-inference mismatch between different engines, then that will naturally and silently turn your RL to be more off policy and hurt your entire training run. And third is also people really care about throughput in your entire RL use cases. If you have higher throughput, that means you essentially get to iterate faster with your different RL experiments, and then you get more utilization with your GPU as well. So to address the first challenge, we have been working very closely with most of the environment suppliers. And then Miles right now already natively support most of the open source RL environments, including Harbor, like OpenInf, like Prime Intellect verifiers, and Daytona, and also like NemoGym, and also Agentic, which is used by recent Kimi K3 post-training. For correctness, there has been one of the Miles' biggest focus to ensure the train inference mismatch will be alleviated. There are different ways to reduce that. One is just to introduce deterministic kernels in your inference engine, which is a like prerequisite to actually ensure 0 KL for the inference and train engine to make sure you get exact match in your inference and training engine here. There are also things related to chat template fixing, where token in, token out make sure that your multi-turn agentic chat templates will be all aligned, and then all the tokens will be matching the prior turns tokens without any train inference mismatch as well. And third thing is related to algorithm fix. There have been routing replay and also truncated mask importance sampling. Those are all techniques to enable stable training with large-scale MOE for reinforcement learning stage. And fourth is also more engineering-driven. It's mostly, we have day zero support for most of the models, and they are all verified with our own training routes. Where whenever we support new models like Inkling, like Kimi K3 training, we always have our own in-house training route to make sure the KL is controlled, the reward goes up, so that people can use the framework directly without any concern. Okay, so lastly, for high throughput, like Ashla and Miles are also like keeping improving around that. We basically have much sophisticated and like mature support for fully async RL, which get to, compared with synchronous case, basically we get to overlap the time for rollout and train, and also disaggregate those two settings to make sure those are making best use of your GPU. And also we have very heavy investment in low precision training, where your rollout will be in a lower precision, and your training backend will be with some type of like quantization-aware training. So that enables us to train with lower precision in rollout stage, where we natively support like 8-bit and also 4-bit training. And in this case, we also recently worked with Humans End to support NVIP4 native rollout in RL stage without any performance loss. Okay, as a summary, we are producing and working on Ashla and Miles, and then we welcome everyone to contribute, work with us, and try that, provide feedback. So please also take a look at both projects, and then we'd love to hear more from you. Thank you.
All righty. Thank you, Benghua. Next up, we have, let's see, Ranjan Sinha with IBM. Thank you.
Okay. Well, hi, everyone. So when agents speak in different languages, you need to write custom code, glue code, adapters, and that doesn't really scale too well. So, and that's really the Tower of Babel problem. So NLIP is the universal handshake that makes seamless interoperability real. So if the agent speaks NLIP, it speaks to everything else that does. So think of NLIP as the HTTP of intent. And it follows a very similar approach of being minimal and neutral. So HTTP is a neutral, uniform way to transfer resources between heterogeneous clients and servers. And NLP is a neutral, uniform way to transfer meaning or intent between heterogeneous agents and clients. So it came out of a working group of academia and industry, researchers and practitioners. And it was sponsored by the Enterprise Neurosystems Group and the AI Alliance. And it is now a ECMA standard, and TC56 is the technical committee that drove NLP. And JavaScript was also standardized by the ECMA body. And some of the contribution organizations are on the right-hand side. Now, the AI-based software systems or agents are being deployed in a wide range of applications. So agents serve different functionalities and operated by different organizations. They must interoperate through a common communication protocol. So let's look at the left diagram. So a traditional protocol. So agent 1 speaks language A, agent 2 speaks language B, and what passes over the wire is language P. Now, in a traditional protocol, they all have to be the same. So A is equal to P is equal to B. And if there is any change in the schema or change in fields, it typically breaks. And that's really the hard-coded integrations, and that is tight coupling. And that creates issues with interoperability, version management. And if you look at the right-hand side, that's the domain, that's where NLP comes into the picture, where you have agent 1 that speaks language A, agent 2 speaks language B, and what passes over the wire is P. And A doesn't have to be equal to B, doesn't have to be equal to P. So it promotes flexibility. But the condition is that there needs to be intelligence at both endpoints, so it can translate between these messages. And given the current trends, you'd expect intelligence to be available in solutions and systems, and it continually improves. So NLP provides a very simple, open, common, standard protocol for applications, agents, and services to communicate with each other. It assumes intelligence at both endpoints to enable the semantic understanding, and it follows the request and response paradigm to ensure that the meaning or intent is refined and confirmed before the agent gets to act on it. And if a message is ambiguous, it will, the agent doesn't just fail, it will ask for clarifications. So that's really the request response paradigm. And it is built for enterprise reality. So if you deploy an enterprise or otherwise some serious application, some of the requirements for the protocol are on the right-hand side. It needs to be secure, got to have safeguards, it's transport agnostic, and essentially it uses the existing infrastructure. It's not rebuilding the wheel. Suppose multimedia communication is efficient. I have some charts to show that. It can be implemented in multiple languages, and it is an open standard governed by ECMA. And we've also submitted that for the ISO standardization, and so that's currently in progress. Great. So now coming to the NLP specifications, it is deliberately minimal. So if you see the message model, it's a lightweight JSON. It is just 5 fields. And out of these 5 fields, 3 are mandatory. So you have the content, which essentially is a lightweight JSON envelope, which contains the information that is exchanged. The format is, you specify, is it text? Is it structured? Is it binary? And then your subformat is essentially a refinement. If it's text, what language that text is in, and encoding for a binary content. And then there are 2 optional fields that suggest a parsing hint, and you can have more additional content in the sub-message. But that's really it in the core and data model, these 5 fields. And if you compare with some of the more popular protocols that's used, let's say A2A or MCP, you're looking at 60 to 99 to the full data model having 166 to a 480 fields. So in that sense, it's very lightweight. And in terms of, it's very simple to implement over standard transports. So you have the bindings for HTTP, for WebSocket, for AMQP, and these are specified in the ECMA specifications, and you can access that from the GitHub page. And it is secure by design, so it's mandatory. So you have 3 profiles, from basic to rigorous enterprise profiles, and addresses various AI-specific risks, besides just the transport security. Now, NLIP can interoperate with various single vendor protocols in 2 modes. The first mode is NLIP is a northbound API, and single vendor protocol a southbound API, and you use the translation agent LLM powered to translate between these 2. And in mode B, if it can interoperate across multiple domains, and each of these domains you can have multiple agents that speaks in their own language using different agent frameworks. But as long as they are NLIP aware, they can all communicate with each other. And so this is a very powerful feature. Now, several proof of concept applications have been developed by companies and universities and across multiple domains. So you have telecom to shopping to sustainability to multimodal customer support and so on. And a lot of these are also available on the project page. So I'll dive a bit deeper into the customer support, where in this case, a customer submits a voice request. It's a query. That is then, it's an audio. That's then converted to text using a speech-to-text model, NVIDIA ASR. That is then, we then use NLIP over HTTP and send that information to the channel recommender, which picks up the most relevant subreddit channels for that query. That's then sent using NLIP over HTTP to the search agent that picks up the most relevant topics from those channels, ranks them, and sends it back to the customer. Essentially, a customer query picks up the most relevant topics from Reddit, and the customer gets those responses. So we compare NLIP with A2A for this workflow, and we use a very similar symmetric identical timing harness for NLIP and A2A, and we use 3 variants of A2A. And we also have phase-level instrumentation, that's message creation, connection, and send to really understand where timing is going. And the total latency is really a summation of these 3 phases. We use 2 machines, 2 data sets containing several customer queries. And so the average total latency across the queries on both the phases where we use NLIP, you'll see the NLIP is in blue, and then you have variants of the A2A SDK to cache-optimized A2A to a lightweight Python A2A on the right-hand side. And you'll find that it's the minimal nature of A2A is displayed here. Of course, I would say it's preliminary experiments. You can do a lot more complex workflows and experiments, and that's something that we like to do. And if you'd like to participate, that'll be terrific as well. But it gives you a sense as to it's a very lightweight message envelope. Now, for practitioners, it will boil down to when do we use these protocols. So you can choose NLIP when you're looking at, when you have a use case that is around, requires heterogeneous protocol interoperability, or semantic flexibility, or cross-protocol mediation, and choose A2A when you have governance and audit needs, or task-centric, or long-running workflows, strict schema enforcement, deterministic execution, and you can even choose a hybrid when you have mixed workloads, and NLIP at the coordination layer, and then A2A at the governance layer. These are various guidance that we are working on based upon our experiments and evaluation. But the important thing here is that the protocol selection should be guided by the workload characteristics. Currently, we have several protocols, essentially long-tailor protocols. You have domain-centric protocols being introduced for payments and shopping and so on. So how do we work across these protocols and communicate in an interoperable manner? And that's where the NLIP fits in. So to summarize, it's a standard-based semantic protocol that connects clients to agents. and bridges different agent protocols. It's simple, it's open, it's lightweight, it's neutral, and think of it as the HTTP of intent, and it is built for the intelligence era. And in preliminary experiments, we observed that it was efficient during message creation and transport. And for practitioners, you can choose NLib based upon agent workload characteristics. Now, you'll find the details of NLib on the project page. It has been integrated with AG2 framework as well. That's downloaded tens of thousands of times daily, probably 1 million in a month. So if you're interested in your feedback, of course, we always welcome that. It's a very active committee. We meet weekly and continue to develop this protocol. And if you have any use cases in mind, participate in evaluation or contribute to NLib, we'd love to hear from you on that. So there are emails and other contact details on the project page. So with that, thank you very much.
All right, thank you, Ranjan. That's it for Atlas Stage today. So thank you, everyone. There's reception and poster presentations on the first floor if you want to check those out. And then tomorrow we have a bunch of new talks in enterprise AI, agent evaluation, benchmarks, as well as AI for math. So see everyone tomorrow. Feel free to walk to Zellerbach, other places, or go to the first floor. Thank you.